This video will quietly shatter everything you thought you understood about the universe. Because in physics, what feels obvious is often completely wrong. Time doesn't always move at the same speed. Objects can be in multiple places at once, and the chair you're sitting on right now, it's made almost entirely of empty space. Tonight we're going to drift through the strangest truths in science, gently, slowly, without any rush. So before we begin, where are you listening from right now? Let us know in the comments. And if you enjoy these calm journeys into the weird side of physics, help us reach 150 subscribers by hitting that button. It really supports what we're building here. Now take a deep breath, get comfortable, and let's begin with the first idea that breaks everything you thought you knew. Time doesn't tick the same for everyone. Chapter 1. Time moves slower when you move faster. Time has always felt like the one thing we could trust. The ticking of a clock, the sun rising and setting, a heartbeat. From the moment we are born, we grow used to the idea that time moves forward, steadily, for everyone. But the truth, hidden in the laws of physics, is that time is not a constant. It can stretch, it can slow down, and it can break away from what you thought was real. This is the story of time dilation, one of the most quietly disturbing discoveries in all of science, and it began with a question so simple, it barely seemed worth asking. What happens when you move very, very fast? In 1905, Albert Einstein proposed his theory of special relativity. At the heart of this theory was an idea that broke common sense into pieces. The speed of light is always the same, no matter how fast you're moving. This seemed impossible. You're riding a train and throw a ball forward. The ball's speed adds to the train's speed. That's what our intuition says. But light doesn't follow that rule. Whether you're standing still or flying at thousands of kilometers per second, the light you see always travels at exactly the same speed, about 300,000 kilometers per second. That simple truth forces a kind of cosmic trade-off. If light speed never changes, then space and time must bend to make it so. And that bending leads to something strange. If you start moving faster and faster, especially at speeds close to the speed of light, time begins to slow down for you, compared to someone standing still. This isn't a theory. This is a measured, tested, and confirmed phenomenon. Time literally ticks at different rates, depending on how fast you are moving. To visualize this, physicists often use something called a light clock. Imagine two mirrors facing each other, with a beam of light bouncing between them. Every time the light hits the mirror, one tick goes by. If you're holding the light clock and standing still, the light just bounces straight up and down. But now imagine the clock starts moving sideways, say on a fast spaceship. To an outside observer, the light now has to travel diagonally, tracing a longer zigzag path between the mirrors. But light speed can't increase, it's fixed. So to make the journey take longer, the only solution is for time itself to slow down inside the moving clock. This is not just an idea on paper, it has been tested at the real world. In one experiment, scientists synchronized two atomic clocks, the most precise clocks ever built. One was kept on Earth. The other was placed on a jet aircraft that flew around the world. When the clocks were reunited, the one that had been flying had ticked slightly fewer times than the one that stayed on Earth. Just by moving fast, it had experienced time more slowly. Another version used satellites. The GPS system you use every day has to account for time dilation, or your map would be off by kilometers. Now imagine this on a bigger scale. An astronaut traveling near the speed of light might only age a few years, while centuries pass on Earth. This is not science fiction. This is built into the structure of space and time. Time is not absolute. There is no universal clock ticking the same for everyone. Instead, your experience of time depends on how you are moving, and how close you are to sources of gravity, as we'll explore later. It's unsettling, because it means there is no single now. If you and someone else are moving at different speeds, you may disagree about what events are happening at the same moment. A flash of light that seems to hit two walls at the same time for one observer might appear to strike one wall first, then the other, for someone moving past. Time is not something you can peel away from motion. They are part of the same fabric, space. Einstein's insight rewrote everything. Space and time are not separate. They bend together to preserve the speed of light. The faster you move through space, the slower you move through time. And if you could move at the speed of light, which no massive object can, time would stop completely from your perspective. A photon, in theory, experiences no passage of time at all. This leads to strange, quiet implications. A particle born in the heart of the sun, traveling toward Earth, may take thousands of years to arrive in our frame of reference. But in the particle's own frame, where time has nearly stopped due to its incredible speed, that journey may feel instant. 2 moments, separated by millennia to us, could be simultaneous to it. And yet, both perspectives are valid in their own frame. If this is making your head spin, let it. Because physics isn't here to comfort your expectations. It's here to show you what's really there, even when it feels wrong. And the truth is, time is not a river that flows equally for everyone. It's more like a landscape, one you move through, shape and bend depending on your speed. Even the idea of aging becomes flexible. In deep space, a spacecraft traveling near light speed could preserve its crew for generations, while thousands of years pass outside. In science fiction, this is used for time travel, but in real physics, it's simply a side effect of the rules we live in. You don't need a time machine, you just need speed, enormous speed. So next time you look at a clock, remember, it's not the keeper of some cosmic truth. It's just a local measurement, something that ticks in your particular corner of the universe. Someone moving faster than you is aging differently. Someone deeper in gravity is experiencing a different timeline. Time is not one thread, but many. And with that quiet, strange truth, we leave behind the ticking seconds and move into something even stranger. What if a particle didn't have one position, but many? What if it was everywhere at once, until you looked? That's where we're headed next, into the shadows of superposition. Chapter 2. Particles that are everywhere, until you look. Imagine a tiny particle, something far smaller than dust, smaller even than an atom. You might assume that this particle exists in a single place at a time, just like every object you've ever touched or seen. But in the quantum world, the rules are different. Very different. This tiny particle doesn't sit still. It doesn't have one location. Until you look, it exists in a strange, ghostly cloud of probabilities. This is the idea of quantum superposition, a concept that feels more like a riddle than a fact. And yet, it is one of the most precisely tested and deeply unsettling truths in all of physics. A single electron can exist in multiple positions at once. A photon can travel many paths simultaneously. An atom can spin in 2 opposite directions at the same time. This isn't metaphor. This is reality. Let's begin by imagining a simple particle in a sealed box. If you could somehow measure its position without opening the box, you might find it near the left side. Try again, and it might be closer to the right. Repeat the experiment enough times and you'll notice a pattern, a probability distribution. But here's the strange part. Before you measured the particle, it wasn't just hidden. It didn't have one single position at all. According to the mathematics of quantum mechanics, the particle's state is described by a wave function, a kind of map of where it might be, not just where it's likely to be, but all the places it exists simultaneously, in a haze of potential. It's not until a measurement is made, until something interacts with the particle, that its position becomes definite. Before that, it is not in one place, it is in many. This is not just theory. It has been demonstrated in the real world, in an experiment so strange it has become legendary, the double-slit experiment. It begins with a beam of light, or electrons, fired at a screen with 2 narrow slits. On the far side, a detector records where each particle lands. You might expect 2 clusters to form, one behind each slit, but that's not what happens. Instead, you see a pattern of light and dark stripes, an interference pattern, like ripples in a pond. This pattern suggests something astonishing. Each individual particle behaves not like a tiny bullet, but like a wave that passes through both slits at once, a wave that interferes with itself. In other words, each particle on its own travels 2 paths at the same time. It exists in 2 places. It takes 2 routes. It is in superposition. But there's a twist. Place a detector at the slits to observe which one the particle goes through, and everything changes. The interference pattern disappears. The particle now behaves like a normal object, choosing just one path. It's as if the act of looking collapses the particle's wave of possibilities into a single outcome. This moment, the collapse of the wave function, is one of the great mysteries of physics. What causes it? Why does observation matter? Does the universe somehow know when we are watching? Some physicists say it's just interaction, that any measurement, any contact with the environment, forces the particle to make a choice. Others suggest deeper, stranger things. Some theories say that all possible outcomes actually happen, but in separate universes. In one world the particle goes left, in another, it goes right, and in yet another, it goes both ways. This is the many worlds interpretation, a view that says reality constantly branches with every quantum event, creating endless versions of you, of me, of everything. It sounds like science fiction, but it's a serious proposal. But even if we don't go that far, one thing is clear. In the quantum world, particles are not things with definite properties until they are observed. They exist in blurred, probabilistic states, not this or that, but both, not here or there, but everywhere their wave function allows. And yet, when you look, you always find a single definite result. This disconnect between what is and what we observe is what makes quantum physics so unsettling. It tells us that reality at its deepest level is not solid. It's not made of things that exist in a single way. Instead, it's built on uncertainty, on probabilities, on clouds of possibility that don't become real until you ask a question. Measurement doesn't just reveal something, it helps create it. Even more disturbing is that large objects, things like chairs, cats, or people, are made entirely of quantum particles, and those particles all obey the same strange rules. So why don't we see cats in multiple places at once? Why don't humans exist in a haze of probability? The answer is decoherence, the process by which quantum superpositions vanish when interacting with the environment. The more particles an object has, and the more it interacts with its surroundings, the faster its quantum weirdness disappears. It's not that the rules change, it's that quantum effects become smeared out, hidden by noise, drowned in complexity, but those strange rules are still there, beneath everything. Even you are a cloud of quantum fields, temporarily stable, briefly certain. The implications of this are vast and poetic. At the smallest level, the universe is not made of things, but of possibilities. Reality is not a set of facts but a shimmering field of potential, waiting for attention, interaction, or collapse. In a sense, every act of observation brings the world into being, not from nothing, but from the uncertainty that lies beneath everything. It also means that the universe may not be fully determined. If particles behave probabilistically, if even a perfect equation can only give us a range of outcomes, then the future is not fixed. It is guided by likelihood, not certainty. That's why quantum physics allows randomness at the deepest level. And yet, out of this randomness emerges structure. The laws of physics are precise. The constants of nature are finely tuned. The universe, built on uncertainty, still produces stars, planets, minds. This is the strange harmony of quantum mechanics. Uncertainty at the core, order on the surface. Chaos becomes pattern, probability becomes life. So the next time you flip a coin, or watch dust float in the air, remember, underneath everything you see is a world of particles in multiple states. A world that does not fully decide what it is until you look, and even then your act of looking might be shaping the reality you think you're observing. This is not science fiction, this is the world we live in. Chapter 3. You are mostly empty space. You touch the world every day, the ground beneath your feet, the cup in your hands, the air that brushes your skin. Everything feels solid. You trust that when you sit on a chair, it will hold you, that when you lean on a wall, it will not let you pass through. But here is the quiet truth that physics reveals. None of it is solid, not really. Everything around you, and everything within you, is made up of atoms. Those atoms form molecules, and those molecules form the structure of your body, your home, your world. But what are atoms made of? And how much of that structure is actually nothing at all? Let's start small. An atom consists of a central nucleus, made of protons and neutrons, surrounded by a cloud of electrons. If we imagine the nucleus as a grain of sand placed in the center of a cathedral, the electrons would be orbiting somewhere near the outer walls. Between them, just empty space. The distance between an atomic nucleus and its electrons is vast compared to their size. More than 99.999999999% of the atom is empty. And since you are made entirely of atoms, so are your bones, your blood, your thoughts. You are, in every physical sense, made almost entirely of empty space. And why do things feel solid? Why doesn't your hand pass through your desk? Why don't you fall through the floor? The answer lies not in physical contact but in invisible forces. When your hand approaches a surface, the electrons in your atoms repel the electrons in the surface. It's not because they touch, it's because of electromagnetic repulsion. What you feel as solidity is really the resistance of invisible fields. You never truly touch anything. The sensation of touch is the result of your nerves detecting electromagnetic interactions between electron fields. Your body interprets that resistance as pressure, texture, weight, but on a subatomic level, there is no contact, just forces resisting proximity. The atomic nucleus is incredibly dense, but it occupies almost no volume. If you removed all the empty space from the atoms in your body, you could be compressed to a volume smaller than a grain of rice. And the same is true for the entire human race. If you compressed all 7 billion people by removing the atomic gaps, the resulting mass would fit inside a sugar cube. The universe is not built from solid brick, it's built from structured emptiness, patterns of energy, wrapped in fields, governed by probabilities. Matter only appears solid because of how those energies behave when brought close together. Solidity is an illusion, a useful one, but still an illusion. Even the particles themselves are not what we once imagined. Electrons are not tiny marbles, they have no known size, no internal structure, they are point-like, with mass, charge, and behavior, but no surface. And even those points are not fixed in space. The location of an electron is defined by a probability field, a region where it is likely to be found. So when we speak of an object being there, what we really mean is that a large collection of mostly empty fields is statistically likely to appear in that place, at that time. Solidity is what happens when enough of those fields resist being overlapped. It's not because there's something there, it's because something pushes back. Reality is relational, not absolute. This has strange consequences. If you could remove the repulsive forces between atoms, you could walk through walls, you could pass through the earth as easily as light through glass. The only reason we cannot is because quantum forces prevent atoms from overlapping. You may have heard of the Pauli exclusion principle, a rule in quantum mechanics that says no two electrons can occupy the same quantum state. This is not just a detail, it's why matter holds its shape. Without this rule, electrons would collapse inward, atoms would flatten, and all the empty space in matter would vanish. Everything would fall into itself. It is this invisible scaffolding of rules and forces that holds the world together, and yet, beneath that scaffolding is a vast humming emptiness. The solid things you rely on are just vibrations, patterns, and interactions, not objects in the way we were taught to imagine. Physics doesn't strip away meaning, it reveals how deep the mystery goes. Even deeper than atoms is the idea of quantum fields, the strange belief that particles are not little pieces of matter but excitations in an underlying field. What we call an electron is really just a ripple in the electron field, a photon, a ripple in the electromagnetic field. These fields are everywhere, even in empty space. When you see nothing, you are still seeing something. Empty space itself is not truly empty. Quantum fluctuations are constantly bubbling in and out of existence. Particles and antiparticles appearing for a fleeting moment, then disappearing again. Even in perfect vacuum, energy never truly rests. This is the quantum foam, the restless energy of nothingness. So what are you? A body of fields and energy held together by electromagnetic repulsion and quantum exclusion. A swirling structure of probabilities that only appears solid from the outside. Beneath the surface you are space. Beautiful, structured, vibrating space. This view doesn't diminish your reality, it enriches it, because it means that solidity is not a given, it's a miracle. It means that the world you walk through, and the body you live in, are delicate constructions on the edge of what could fall apart. You are balanced, not fixed, emerging, not final. And if everything is mostly empty, what happens to time in all that space? Is there a universal now that fills it? Or does time, like matter, depend on where you are and how you move? Chapter 4. The present doesn't exist. At least not for everyone. Close your eyes for a moment. Think about now, the moment you're in. The ticking instant you call the present. It feels obvious, shared, universal, as if everyone in the universe is passing through this exact moment with you. But what if that feeling is an illusion? In our daily lives, we think of time as a shared dimension, like a river that flows the same way for everyone, everywhere. But in physics, particularly in Einstein's theory of special relativity, time behaves differently. It becomes relative, it warps and stretches depending on how you move. And when that happens, something very strange follows. There is no single absolute present. To understand this, imagine two people, one standing still on Earth, and the other zooming past in a spaceship at near light speed. Both are alive, breathing, thinking. Each of them experiences time in their own frame of reference. But what they consider to be now, that fleeting slice between past and future, will not line up. Events that seem simultaneous to one may appear sequential to the other. This is called the relativity of simultaneity, and it is one of the most quietly shocking ideas in physics. It tells us that now is not something that spans the universe. Instead, it is a localized experience, shaped by your motion and position. What is happening at this moment for you may already be in someone else's past. Let's go deeper. Imagine you're on a train, moving quickly along a track. There's a lightning strike at the front of the train, and another at the back, at what seems to be the exact same time. If you're standing on a platform watching the train pass by, and you see both strikes happen simultaneously, it makes sense. But someone riding on the train will perceive the lightning at the front and back as happening at different moments. Why? Because light has a finite speed. If you're moving toward one flash and away from the other, the light from each strike reaches your eyes at different times. In your frame of reference, one flash came before the other even though someone else saw them at the same time. Both perspectives are valid. Neither is more real. This simple scenario reveals something profound. There is no single agreed-upon present moment that stretches across all space. Instead, every observer, based on their motion, slices space-time different. The universe has no shared now. This can be hard to accept. We like to think there's a single timeline, a shared experience of time, ticking forward for everyone together. But the universe does not care about our intuitions. It allows each observer to carry their own version of time and their own sense of what is present. This also affects how we think about cause and effect. If two events happen far apart in space, and there's no signal fast enough to connect them, the order in which they happen depends on how you're moving. For one person, A comes before B. For another, B comes before A. Time itself is not a universal sequence. But what about the Big Bang? Didn't the universe begin at a single moment, shared by everything? Not quite. The Big Bang didn't explode into space. It happened everywhere, because space itself was born from it. And just like now, the beginning of time looks different from different perspectives. So where does that leave the present moment? If there is no universal now, what are we experiencing when we feel like we're in this moment together? The answer is something local, something personal. Your present is defined by your position in space-time, and by the speed at which you're moving through it. In fact, some physicists believe that all moments past, present, and future already exist. According to the block universe interpretation of relativity, time is like space, a dimension where all events simply are. The future is not something that hasn't happened yet. It's something that exists, just not in your current slice of space-time. This idea treats time as a landscape, not a flowing river. You are not a traveler moving through time. You are a being stretched across time, like a worm in an apple, present at different moments depending on your frame of reference. The moment you call now is just one cross-section of that larger existence. Others elsewhere might experience a different slice. This makes our everyday language about time feel awkward. We say things like the past is gone, or the future hasn't happened yet. But those statements assume a single timeline. Physics says there are many. And what is past for you could still be happening for someone else. Even your memory of the present is unstable. Neuroscience shows that what you experience as now is actually a brief window of time about 2 to 3 seconds long. Your brain stitches these seconds together into a continuous flow, giving the illusion of a moving present. But that motion is just your mind's way of interpreting events. When we combine that with physics, it becomes clear. Now is not a sharp point. It is a blur, a perspective, a frame of reference that moves with you and changes depending on your speed and position. Time is not a universal pulse. It is a weave of many overlapping timelines, and we are each moving through our own. So the next time someone asks, "What time is it?" know that the answer is more complicated than any clock can tell. Because in the fabric of space-time, there is no single present. There are only perspectives and the paths we take through them. Each path carves its own sense of now. Chapter 5. The universe has no center and no edge. If someone tells you the universe is expanding, the natural question that follows is simple. Expanding into what? Where is it going? Where is the center? Where are the edges? But the moment we try to imagine space as a thing, as a box that holds the cosmos inside it, we've already made a mistake. The universe is not expanding like a balloon inside a room. There is no room, there are no walls, there is no center, and no outside to expand into. Space itself is expanding, and that means every point in the universe sees itself as the center, because every point is moving away from every other. It isn't a trick of perspective, it's how space-time works. Let's start with what astronomers actually see. When we look into the night sky, we see distant galaxies. Many of them are moving away from us, and the farther they are, the faster they recede. This discovery, first made by Edwin Hubble in the 1920s, became one of the foundations of modern cosmology. The light from distant galaxies is stretched, shifted toward the red end of the spectrum. This is called redshift, and it tells us that space itself is expanding. But expansion doesn't mean there's a central explosion point. The Big Bang didn't happen at a location in space. It happened to space. Everywhere. All at once. Every region of space was once compressed into an incredibly hot, dense state, and as time moved forward, that space expanded. To understand this more clearly, imagine a loaf of raisin bread baking in the oven. As the dough rises, every raisin moves away from every other raisin. But there is no single raisin at the center of the expansion. No matter which raisin you live on, all the others appear to be receding. The universe works the same way, except in 3 dimensions, and without any dough outside the loaf. There is no outside. Space itself is what is growing, and because it is space, not objects within space, that is expanding, there is no edge either. There's no place you could stand and say, this is the end of the universe. But what about the observable universe? The part we can see? Isn't that a kind of edge? Not exactly. The observable universe is not the limit of the cosmos. It's the limit of what light has had time to reach us, given the age of the universe and the speed of light. Beyond that horizon may lie countless galaxies, maybe even infinite space. We simply can't observe it yet. And that horizon is not fixed. Every day, light from more distant galaxies reaches us for the first time. Our observable universe is constantly growing, not because the cosmos is changing, but because our view is. It's like walking into a foggy valley. The longer you walk, the more you can see, but the valley was always there. So, if the universe has no center, where did the Big Bang happen? It happened everywhere. The Big Bang was not an explosion in space. It was the rapid expansion of space itself. There was no pre-existing room for it to explode into. Space, time, matter, and energy all emerged together. And they're still stretching, still unfolding. The image of a balloon being inflated is helpful, but we must remember what it represents. The surface of the balloon stands for space. A 2-dimensional surface, with no center on the surface itself. Every point moves away from every other point as the balloon expands, but the balloon is expanding into a higher dimension, something we don't observe in our universe. In reality, our universe may not be embedded in anything. That's hard to imagine. Our minds want a container, a boundary, a box to put things in. But the universe doesn't need a box. It doesn't need a surrounding. It is everything, by definition. Asking what's outside the universe is like asking what's north of the North Pole. There's another surprising consequence. Because there is no center, every point in space looks like the center from its own perspective. If you were living on a galaxy a billion light-years away, you would see the same redshifts we do, and the same evidence that the universe is expanding away from you. Every point is the center of its own observable universe. This leads us to a beautiful idea. The laws of physics do not privilege one location over another. The cosmos is not arranged around a chosen center. It is not built around us. We are not in a special place, and that, in a way, makes our place even more special. Because the more we learn, the more we realize how strange and democratic the universe truly is. It expands not from a point but as a whole. It has no center and no edge, no middle and no outside, only space, stretching in every direction. A universe without a boundary, but full of motion. And what lies beyond what we can see? Perhaps more of the same. Perhaps regions where space curves differently, or where the laws of physics are slightly altered. Or perhaps nothing at all. A true void, unreachable and unknowable. Yet even if we cannot touch it, the idea expands our minds. It forces us to let go of borders, to stop imagining a universe contained in a box. The cosmos may be infinite, or it may wrap around itself like the surface of a sphere, finite but unbounded. Either way, there is no wall, no edge to fall from. So the next time you look up at the stars, don't ask where the center is, ask where you are, and know that, from your point of view, the universe is growing around you. And from every other point it's doing the same. A cosmic expansion without a middle. Chapter 6. The universe is built on symmetry and broken balance. There is a quiet order hiding behind the chaos of the cosmos. Beneath the explosions of stars and the flicker of quantum fields, something deeper hums like a melody beneath noise. It is the principle of symmetry, a hidden architecture that shapes the behavior of everything. And yet, strangely, it is the breaking of that symmetry that gives birth to the world we know. In physics, symmetry is not just about appearances, it is a rule, a constraint that governs what can and cannot happen. When a system obeys a symmetry, it means that changing certain things leaves the laws of physics untouched. You can rotate it, shift it, reflect it, and the outcome remains the same. The rules do not care where or when you are. One of the most important examples is translational symmetry. This says that the laws of physics are the same in every location. What happens here could happen there. Because of this symmetry, momentum is conserved. It cannot be created or destroyed, only transferred. This is not a coincidence. It's a consequence. The same is true of time symmetry. If the laws of nature do not change over time, then energy is conserved. This is not a philosophical idea. It is a mathematical theorem. In the early 20th century, mathematician Emmy Noether proved something extraordinary. Every symmetry in the laws of physics corresponds to a conserved quantity. It's called Noether's theorem, and it tells us something profound. The universe doesn't just behave consistently, it must. The regularities we see are born from deeper patterns that cannot be violated. Conservation laws are not imposed by hand, they emerge from the symmetries of nature. But not all symmetries remain unbroken. In fact, some of the most interesting features of the universe come from the fact that certain symmetries are broken, and that breakage gives rise to structure, to motion, to matter. In other words, imperfection is not a flaw. It is the engine of reality. And nowhere is that more true than in the early universe. In the moments after the Big Bang, the universe was incredibly hot, dense, and symmetrical, forces that are now distinct, like electromagnetism and the weak nuclear force, were unified. They were different faces of the same fundamental interaction. But as the universe cooled, that symmetry broke, the forces split, and suddenly new structures could form. Symmetry breaking gave rise to diversity. This happens in everyday physics too. Consider a simple example, a pencil balanced on its point. It's symmetric in all directions, until it falls. When it tips over, it chooses a direction. The symmetry is broken. That break is not random. It's a transition from a higher symmetry to a lower one, and it creates order from instability. In quantum physics, the same principle applies. The famous Higgs mechanism relies on a broken symmetry in the Higgs field. As the universe cooled, the field settled into a non-zero value, and in doing so it gave mass to certain particles. Before that moment, mass did not exist. This means that everything with weight, from atoms to stars, owes its mass to a broken symmetry. Mass is not fundamental, it is a result, and that result came from an invisible field, gently falling into a stable configuration after a high-energy beginning. The universe crystallized, and with it, matter was born. Symmetry breaking also explains why there is more matter than antimatter in the universe. At first, the two were created in equal amounts, but somehow, a tiny imbalance formed, just one extra matter particle for every billion pairs. That asymmetry made everything you see possible. If the symmetry had held perfectly, all particles would have annihilated, and nothing would remain. So in this strange way, everything exists because perfect balance was disturbed. The universe chose a direction, fell into a state, and broke the mirror. That broken mirror reflects stars, planets, people, all born from the loss of perfect symmetry. Beauty did not come from order alone. It came from the moment order collapsed. This idea runs deeper still. The standard model of particle physics, the most successful theory ever built, is based on symmetries called gauge invariances. These are rules that say the laws of physics must stay the same even when certain transformations are applied to the fields. These gauge symmetries define the interactions between particles. Without them, we would not have the electromagnetic force or the strong nuclear force or the weak force, and these forces are not just observed, they are required by symmetry. They are the universe's way of keeping its equations balanced when its fields shift and turn. Physics is not made of particles alone, it is made of principles, and symmetry is the deepest of them. Even at the cosmic scale, symmetry rules the structure of space. General relativity, Einstein's theory of gravity, is built on the idea that space-time itself is symmetric under changes of coordinates. This symmetry leads to conservation laws for momentum, energy, and angular momentum. The very shape of gravity is dictated by how space-time refuses to favor one location over another. But symmetry is not only about structure, it's also about information. In quantum mechanics, symmetry determines what can happen and what cannot. It places limits on how particles interact. It tells you which transitions are allowed, which outcomes are possible, and which are forbidden. Symmetry narrows the infinite into the probable, and yet, every meaningful thing you see is the result of symmetry not being perfect. A perfectly symmetrical world would be featureless. No stars, no galaxies, no people. We live in a universe that almost had perfect balance, but just barely didn't, and that is why we are here. Symmetry gives rise to conservation, breaking it gives rise to creation. Between these two, between the perfect and the flawed, lies the canvas of reality, and it is on this canvas that matter paints its forms. Light, mass, motion, all are whispers from the echo of symmetry. So the next time you admire the beauty of a snowflake, or the structure of a crystal, or the curve of a planet's orbit, remember, behind all of it is a tension between what could have been perfect and what actually was. The universe is a mirror cracked with intention, and through that crack, complexity flows. Chapter 7, The Magic of Spin and the Quantum Dance. Close your eyes and picture a tiny particle spinning like a planet, turning quietly on its axis. Now imagine that this particle is not just spinning one way, but two ways at the same time. Imagine that it can't stop spinning, can't be slowed, can't even be pictured properly in space, because what it's doing isn't like anything you've ever seen. This is quantum spin, and it will break every mental model you've tried to build. Spin is one of the most fundamental properties of particles. It is listed right next to mass, charge, and position, a number that describes how a particle behaves. But unlike classical spin, it has nothing to do with a particle physically rotating. Quantum spin is stranger. The term spin is a bit misleading. It was borrowed from the behavior of larger objects, because when scientists first studied electrons, they noticed that these particles generated magnetic fields, the same way spinning charged balls would. But as they learned more, it became clear, electrons are not tiny balls. They have no size. They are point-like, with no internal structure, and yet they behave as if they are spinning. This behavior is not just metaphorical, it is quantized. Electrons have a property called spin 1/2. That number doesn't mean half a spin. It's a label, a way of identifying what kind of particle it is. And here is where things get strange. If you rotate an electron by 360 degrees, it does not return to the same state. Let that sink in. Spin a planet, or a basketball, or a coin, and one full turn brings it back to where it started. But an electron, a full turn only gets you halfway. You have to rotate it 720 degrees, 2 full spins, before it behaves the same again. No classical object acts this way. This is not a quirk. It is a feature of spinos, mathematical objects that describe particles with half-integer spin. These spinos are deeply tied to the geometry of quantum fields. They obey different rules from vectors, and their transformation under rotation is uniquely quantum. They are not illustrations, they are equations, and they match what we see in every experiment. The universe follows these rules, even if we can't imagine them. That spin isn't just about strange rotations, it determines how particles behave when they are brought together. Fermions, particles like electrons, protons, and neutrons, have half-integer spin, and they obey the Pauli exclusion principle. That means no two fermions can occupy the same quantum state at the same time. Because of this, matter has structure. Electrons stack into orbitals around atoms. Protons and neutrons arrange themselves inside nuclei. Without spin and the exclusion it enforces, matter would collapse. There would be no chemistry, no molecules, no life, all from a hidden quantum number, deeper than mass or charge. On the other hand, particles with integer spin, like photons, are called bosons. They behave differently. They love to cluster, they can occupy the same state without restriction. This is why lasers work. Many photons pile into a single wave, marching in perfect rhythm. Bosons are the carriers of forces, fermions are the building blocks of matter. Spin is what separates them. It is the rule that draws the line between things and forces, and it gets even stranger when two spinning particles become entangled. In quantum mechanics, entanglement means that two particles share a single combined state, one that cannot be separated, no matter how far apart they are. And when those particles are spinning, the results become eerie. Imagine two electrons, entangled in opposite spin states. One is up, the other down, but until you measure, neither has chosen. They are in superposition, both up and down, together. Measure one, and instantly, the other takes the opposite value. Even if they are light years apart, the result is instant. This has been tested again and again, and the correlations cannot be explained by any local cause. Einstein called it spooky action at a distance, and to this day, no one fully understands why it happens. But it does, every time. Spin is not just a label, it is a doorway into the non-local structure of reality. In the quantum world, spin affects how particles move, how they bind, and how they behave under symmetry. In fact, there's a deep connection between spin and the fundamental structure of space-time. According to relativistic quantum field theory, particles with different spin values obey different types of equations. Spin 0 particles follow scalar field equations. Spin 1 particles, like photons, obey vector field rules. Spin 2, that's gravity. Yes, if we ever discover a quantum theory of gravity, the graviton would be a spin 2 particle. That's how deep spin goes. It isn't just about how things turn, it's about how reality talks to itself, about how forces arise, about how fields dance in space and time. Spin is not surface level. It's a root. This also explains why particles behave differently under rotations and reflections. Some particles don't care if you mirror them. Others do. In fact, the weak nuclear force famously violates mirror symmetry, called parity violation. It treats left and right differently, and it shows up in how spin determines decay directions. This was one of the first clues that not all symmetries in nature are preserved. That spin, invisible, abstract, and impossible to photograph, affects the deepest rules of nature. What direction something spins can determine whether it exists or not. That is power. That is reality. So when you hear that an electron has spin 1/2, don't picture it as a ball rotating slowly. Picture it as a quantum whisper, a condition of being that controls how it moves, how it binds, how it relates to every other particle in the universe. Picture it not as a rotation, but as a rule, one that the cosmos obeys without fail. Spin also plays a role in quantum computing, where the spin state of electrons or nuclei can be used as qubits, units of quantum information, because spin states can be up, down, or both at once. They allow computations far beyond classical limits. The dance of spin is not just a curiosity, it is the heartbeat of quantum logic, the structure beneath digital thought. And all of this happens in silence. You cannot see spin, you cannot touch it, you cannot separate it from the particle that carries it, but it is there, in every interaction, in every atom, in every field that builds the world. Reality dances, and spin writes the rhythm. Chapter 8. Entanglement, spooky, elegant, and real. Picture two particles, born from the same event. They fly apart, one left, one right, racing away into the vastness of space. Light years may eventually separate them. Galaxies might rise and fall between their paths. And yet, when you measure one, you know everything about the other, instantly. This is not science fiction. It's not a misunderstanding. It is one of the most well-tested and unsettling truths in all of physics. It is called quantum entanglement, and it breaks our understanding of what it means to be separate. Two things, far apart, behaving as if they are one. This is wrong. Entanglement begins with superposition. The idea that a particle can be in many states at once, up and down, here and there, existing not as a fixed point, but as a cloud of probabilities. But when two particles interact, something even stranger can happen. Their states become linked, not just correlated, but inseparable. Imagine flipping two coins at once. Normally, each coin lands randomly. The result of one doesn't affect the other, but entangled coins behave differently. Flip them, and you always get opposite results. One heads, the other tails, no matter how far apart they are. It's as if the outcome is decided together, across space. But in quantum mechanics, it goes deeper. The entangled particles don't even have definite states until you measure them. They are in superposition, both possibilities held at once. Yet when you observe one, its state becomes fixed, and so does the others. This connection is not the result of communication. No signal travels between them, nothing moves through space, and yet the effect is immediate. Einstein called it spooky action at a distance. He disliked it. He thought the theory must be incomplete. But in 1964, physicist John Bell proposed a way to test entanglement. He showed that if hidden variables were responsible, if the particles had predetermined instructions, then certain patterns would appear in experiments, but quantum mechanics predicted different results. Bell's inequalities would reveal who was right. The experiments were performed, then repeated, and repeated again, with photons, with ions, with electrons, across kilometers, with synchronized detectors, and every time, quantum mechanics won. The particles were truly entangled, no hidden variables, no classical explanation. What this means is hard to grasp. Two objects can exist in a shared quantum state that is not the sum of their parts. They are not two separate things. They are one system, stretched across space, and that system only resolves into parts when you look. Even more astonishing, this is not a rare event. Entanglement happens constantly, in labs, in nature, in the machinery of quantum computers. It is not an exotic phenomenon, it is a basic feature of the universe. We are just not used to seeing it. You cannot see entanglement with your eyes. You cannot point to it, but you can measure it. Its presence is mathematical, a signature in the behavior of outcomes. When entangled particles are measured in different directions, their results obey specific patterns, ones no local system could explain. Those patterns are the fingerprints of quantum connection. This doesn't mean you can send messages faster than light. Entanglement doesn't allow instant communication. You cannot control the outcome of a measurement, only observe it. And so, while the results are correlated, they cannot be used to transmit information. But the implications are still profound. Entanglement suggests that space may not be fundamental. If two particles can be joined without proximity, what does it mean to be far apart? Perhaps distance is an illusion, a convenience. Some physicists now believe that space-time itself may emerge from entanglement, that geometry, gravity, and even time are born from the structure of quantum connections. This is not just a theory, it is a growing framework, explored in holographic models and quantum gravity. The idea that the universe is woven together by information, not space. Entanglement also underlies quantum computing. In a quantum computer, qubits are not just bits that are 0 or 1, they can be both, and entangled with each other. This allows computations to be done in parallel, across an entire sea of possibilities. It's not just faster, it's deeper. Quantum teleportation also uses entanglement. By entangling particles and transmitting classical information, it's possible to transfer quantum states from one place to another, not particles, but the state itself, the identity, the information that defines it. It sounds like science fiction, but it has been demonstrated in the lab. And yet, entanglement is fragile. Interaction with the environment can destroy it. This is called decoherence, the process by which quantum states lose their purity. It's why the quantum world feels hidden, why we don't see superpositions in daily life. The more particles involved, the faster entanglement fades. Still, it is everywhere. In the sun's fusion reactions, in the chemistry of photosynthesis, in the bonding of atoms. Entanglement is not a glitch in the system, it is the system, a structure beneath causality. So what does it mean for you? It means that the world is not made of parts. It is made of relations. Nothing exists entirely on its own. Every particle is part of a larger state, and what you observe is always entangled with how you observe it. This idea is not comfortable. It doesn't fit in our classical minds. But it is real, tested, proven. It is one of the few truly unavoidable truths about reality. That what is far can be near, that what is separate can be one, that the universe at its core is connected. Chapter 9. The Quantum Harmonic Oscillator and Universal Rhythm. If the universe has a rhythm, this is where it begins. Beneath the quiet hum of atoms and the shimmer of waves, There lies a structure so simple and yet so deep that it appears across every level of physical reality. It is the quantum harmonic oscillator, the system that pulses, vibrates, and echoes the hidden beat of existence. In classical physics, a harmonic oscillator is something that moves back and forth with regularity. A mass on a spring, a swinging pendulum, a vibrating guitar string. The motion repeats, the energy flows between kinetic and potential forms, up, down, back, forth, forever, in perfect rhythm. But when we shrink this idea into the quantum world, everything changes. The motion is no longer smooth. The energy is no longer continuous. Instead, the oscillator takes on discrete energy levels, fixed steps, not fluid slopes. The quantum world pulses in quanta. The quantum harmonic oscillator is one of the most important models in all of physics. It describes not just springs and particles, but the behavior of molecules, fields, and even the vacuum of space. Every quantum field, the electromagnetic field, the electron field, the Higgs field, behaves like a collection of tiny oscillators. It is the most universal equation you've heard of. Let's break it down. In the quantum version of the harmonic oscillator, a particle is confined to move around a stable point, like a marble in a bowl. But unlike the classical version where the marble could be still at the bottom, the quantum version is never truly at rest. Even in its lowest possible energy state, the so-called ground state, it still vibrates. This is called zero-point energy, the irreducible energy that remains, even when all external energy is removed. It cannot be extracted. It cannot be stopped. It is the universe's minimum heartbeat. Every atom in your body vibrates with this energy. Even when you are asleep, even when you are frozen in place, you are never still. The energy levels of a quantum oscillator are quantized. That means they can only take on certain values, evenly spaced, like rungs on a ladder. You cannot have half a step. You either jump to the next level, or you don't. This structure defines how atoms absorb and emit light. When an electron in an atom jumps from one energy level to another, it emits or absorbs a photon, a particle of light, with a frequency exactly matching the gap between levels. That frequency determines the color of the light. Red, blue, ultraviolet, all are expressions of these quantum jumps. The oscillator sets the tempo. These vibrational states also explain the structure of molecules. The bonds between atoms are like springs, and their vibrations define the molecule's properties. Infrared spectroscopy, a technique used in chemistry and astronomy, detects these vibrations. It reads the music of the molecules. But the quantum harmonic oscillator isn't just a tool, it's a blueprint. It shows us that the universe is not made of static parts, but of systems that vibrate. Every field in quantum field theory is described as an infinite set of oscillators, each at a different point in space. When one of those oscillators is excited, we observe a particle. In this view, particles are not fundamental, they are excitations, little ripples in vibrating fields. The photon is a ripple in the electromagnetic field, the electron is a ripple in the electron field. Every particle you've ever heard of is a temporary vibration, a flicker of motion on a canvas of field. Even more strange is that these oscillators don't need to be excited to be active. As we saw, the ground state still contains energy, and that energy is not zero. This leads to one of the most profound implications of quantum theory: the vacuum is not empty. In classical physics, a vacuum is nothing, a perfect void, but in quantum physics, even the lowest energy state is alive with fluctuation. Pairs of particles and antiparticles constantly appear and vanish. These are called vacuum fluctuations, and they are a direct result of the oscillator's zero-point energy. Even silence is humming. These fluctuations have measurable effect. The Casimir effect, for example, shows that two metal plates placed very close together will experience an attractive force, not because of any external field, but because the vacuum between them is slightly different than the vacuum outside. The geometry changes the rhythm of space, and the plates feel it. The quantum harmonic oscillator also appears in blackbody radiation, the spectrum of light emitted by hot objects. Classical physics couldn't explain why objects don't radiate infinite energy at short wavelengths, but the quantum oscillator solved it. The energy levels cut off the possibilities. They force the spectrum to behave. This was one of the first signs that nature doesn't allow infinite freedom. It sets limits, boundaries, discrete notes in the symphony. The universe is not a blur, it is a composition, quantized, precise. And all of it, the way atoms shine, the way bonds hold, The way fields ripple comes down to this one model, the harmonic oscillator. It is the metronome behind chemistry, electronics, cosmology, a simple equation echoing through complexity. You can think of it as the drumbeat of the quantum world. Not chaotic, not random, but pulsing in patterns, repeating, shifting energy from place to place, always vibrating, never silent. It is the universal rhythm. And like all rhythms, it invites interpretation. Some see it as a mathematical curiosity, others hear music in its logic. But whatever we call it, the truth remains. Reality does not stand still, it oscillates. Chapter 10. The interference pattern that changes reality. Imagine throwing a single pebble into a still pond, ripples spread outward in perfect circles, overlapping and colliding. Now imagine throwing two pebbles at once, a little distance apart. The waves meet, they reinforce each other in some places, and cancel in others. The result is a pattern, a tapestry of light and dark, motion and stillness. This is interference, a phenomenon we understand well in classical physics, in sound, in water, in light. But in the quantum world, interference reveals something far deeper. It tells us that particles are not just points, they are waves, and those waves can interfere with themselves. The experiment that exposed this mystery is simple. A source fires particles, electrons, photons, even atoms, at a barrier with two slits. Beyond the slits is a screen where the particles land and leave a mark. If particles are just little bullets, they should go through one slit or the other. And if that were true, the screen would show two clusters, two piles of hits behind the slits. But that's not what we see, not when the slits are both open. Instead, we see an interference pattern, alternating bands of high and low intensity, a wave pattern, a result only possible if each particle somehow travels through both slits at once. One particle, two paths, a wave of probabilities. This is the heart of quantum mechanics. Each particle behaves not as a single entity but as a probability amplitude, a wave that spreads out, splits and reunites. Where the wave reinforces itself, the particle is more likely to land. Where it cancels, it rarely appears. And the strangest part, even if you fire particles one at a time, spaced seconds or minutes apart, the interference pattern still builds up. The particle is interfering with itself. It behaves as if it explores all possible paths, and those paths interact. But here's where it gets even more unsettling. If you try to observe which slit the particle goes through, even with the gentlest possible detector, the pattern disappears. The wave collapses. The particle chooses a path. And now, instead of interference, you see two clumps. It's as if the particle knows whether it's being watched. But that's not quite right. It's not about consciousness. It's about information. When the possibility of knowing the path exists, even in principle, the interference vanishes. The particle stops being a wave. This is the principle of quantum measurement. Observation doesn't reveal reality. It changes it. It forces the system to commit. And once it does, the range of possibilities collapses into one result. Before the measurement, there were many futures. After, only one. This seems to challenge causality. How can a choice in the present affect what a particle did in the past? That's what it looks like, as if observing the outcome reshapes the history. Some interpretations suggest that reality is not truly defined until observed. Others propose that all outcomes happen in parallel universes. In the many worlds interpretation, each possibility becomes real in a branching timeline. In one world, the particle went left, in another, right, and in all of them, the interference exists. Just not from your limited perspective. You see one slice, but the wave persists in all. There is also a version called delayed choice experiments, where the decision to observe or not is made after the particle has passed through the slits. And even then, the interference pattern appears or disappears based on that late choice. It's as if the particle's past behavior depends on a future action. The timeline bends. Does this mean time flows backward? Not exactly. It means that in the quantum world, cause and effect are not as rigid as they seem. Possibilities unfold together, entangled across time. What matters is not when you measure, but that you do. This raises deep questions. What is a particle if it can explore multiple paths and interfere with itself? What is space if location is not fixed? What is reality if looking at it changes what's real? In standard quantum mechanics, the answer is mathematical. Each path contributes an amplitude, a complex number with a magnitude and phase. These amplitudes add together, not just like ordinary numbers but with interference. Where they align, they build. Where they oppose, they cancel. This is the principle behind Feynman's path integral formulation. In this view, a particle's behavior is the result of all possible paths, each weighted by an exponential function of the action. The particle doesn't choose one path, it tries them all. The sum of those paths gives us the probability of what we see. Reality is not a line, it's a sum. This is how quantum tunneling works too. A particle may have zero classical energy to cross a barrier, but the wave function extends through it, and if that wave function doesn't cancel completely, the particle has a chance to appear on the other side. It's not magic, it's interference. Even in chemistry, interference shapes everything. The shapes of electron orbitals are the result of standing wave patterns. Bonding and anti-bonding orbitals arise from constructive and destructive interference. Molecules are not locked in place, they are held by rhythm. And in light, the colors of soap bubbles and oil slicks come from interference. Waves reflected from different layers interact, enhancing some frequencies and cancelling others. The colors you see are born from path differences measured in nanometers. Vision becomes vibration. So what is the lesson of the interference pattern? That reality is not binary, not either or. It is both and. Until you measure, it is a superposition of possibilities that resolve only when questioned. And even then, what you see is not the only truth. It is the slice you get to live. The rest may still be rippling, just out of reach. Every outcome exists as a wave until it becomes a point. Chapter 11. The Geometry of Light. A Journey Through Photons. Light has always carried mystery. It reveals the world to us, yet remains invisible in its path. We see objects because light reflects off them, but the light itself is not seen until it strikes something. It is the messenger of vision, but also a paradox wrapped in waves and particles. For centuries, physicists debated the nature of light. Was it a wave, spreading like ripples in a pond, or a stream of tiny particles, darting through the air like sparks? The answer, as it turns out, is yes to both, and no to either in isolation. Light is a photon, but that word hides a world of strangeness. A photon is the quantum of electromagnetic radiation, the smallest possible packet of light energy. It has no mass, no rest frame, and no classical trajectory. It moves at the speed of light, always, and can never be brought to rest. It is a particle that behaves like a wave, and a wave that behaves like a particle. When we think of light as a wave, we can describe it with a frequency and a wavelength. The frequency determines the energy, the wavelength determines the color. Radio waves are long and slow, gamma rays are short and sharp. All of them are light, just vibrating at different speeds. But when we observe light in certain experiments, it behaves like a particle. It hits detectors one photon at a time. It can knock electrons off of metal surfaces, a phenomenon known as the photoelectric effect. This effect could not be explained by waves alone. It was one of the first pieces of evidence that light came in discrete packets. Einstein won his Nobel Prize not for relativity but for explaining this effect. He showed that when light of a high enough frequency hits a material, it can eject electrons, but only if the individual photons carry enough energy. Increasing the brightness doesn't help if the frequency is too low. Light must deliver its energy in full, indivisible quanta. So, the photon is real, and yet it resists our metaphors. It has momentum but no mass. It exists everywhere along its wavefront, but registers at a single point when measured. It follows the geometry of space, but not in a straight line the way a classical object does. It obeys the rules of quantum field theory, not Newtonian logic. Photons travel along paths known as null geodesics, the straightest possible routes through curved spacetime. In general relativity, gravity is not a force pulling on light, it is the bending of spacetime itself. Light follows the curvature. What appears to be a bent trajectory is actually a straight path through a warped landscape. This is why massive objects like stars and black holes can bend light. It's not that light is pulled, it's that the space it travels through is shaped differently. During a solar eclipse, the light from distant stars appears shifted, an effect first observed in 1919 and used to confirm Einstein's theory. Gravity bends the geometry, and light traces the line. But light also behaves as if it samples every possible path. In Richard Feynman's formulation of quantum electrodynamics, a photon doesn't just travel from point A to point B. It explores every route, straight, curved, looping, absurd, and all of them contribute to the final result. These paths interfere with each other. The sum determines where the photon will most likely appear. This is not just theoretical. The calculations based on this approach are among the most accurate in all of science. Predictions of quantum electrodynamics match experiments to more than 10 decimal places. Photons are both unpredictable and precise. They live at the edge of what we can grasp. Photons also carry polarization, a direction of oscillation perpendicular to their motion. This is why polarized sunglasses can block glare. They filter out light oscillating in certain directions. But polarization is not just a convenience. In the quantum world, it is another axis of possibility. A photon can be polarized in superposition. Entangled photons often share polarization states. Measure one, and the other falls into line, even across vast distances. The entanglement we explored earlier often involves light. Because photons are easy to manipulate and send, they are perfect messengers of quantum strangeness. Yet, despite all this, we rarely think of light as mysterious. It is everywhere, illuminating rooms, screens, cities. We have harnessed it, tamed it, and encoded information into it. Fiber optics carry internet traffic through glass at the speed of thought. Lasers read data, perform surgeries, and measure time. And all of it rides on photons. But the true nature of light remains elusive. It defies categorization. It refuses to be fully wave or fully particle. It does not obey classical expectation. It is an excitation of the electromagnetic field, a ripple without a resting place. It is geometry made visible. Even time behaves strangely for a photon. Because it moves at the speed of light, from its own point of view, no time passes. If a photon is emitted from a distant star and travels for 1 billion years before reaching your eye, in your frame, that's an immense journey. But for the photon, it begins and ends in the same instant. This leads to a deep question. If a photon experiences no time, does it experience reality? Can something that never ages be said to exist in the way we understand, or is the photon a kind of bridge, a link between events that we interpret through our slower clocks? Photons are also responsible for electromagnetic forces. In quantum field theory, when two charged particles interact, they exchange virtual photons. These are not real photons we can detect, but temporary disturbances in the field, carriers of force. They exist only within the rules of uncertainty. In this view, the world is filled with exchanges of invisible momentum. Charges repel or attract not by pushing and pulling, but by trading ghostly messengers. The photon is not just light, it is connection, a unit of interaction. So the next time you see sunlight fall through leaves or watch the flicker of a candle in the dark, remember, you are not just seeing illumination, you are witnessing the most fundamental messenger in the universe, a particle that is also a wave that never rests, a journey that exists without passage of time. Chapter 12, Superposition, where one thing becomes many. In our everyday experience, something is either here or it is there. A switch is either on or off. A door is either open or closed. The world as we see it is built from distinct choices, one state, one outcome, clear, separate realities. But quantum mechanics tells a different story, one that defies this binary simplicity. At the heart of quantum theory lies a principle that breaks our common sense. It is called superposition, and it describes the ability of a quantum system to be in multiple states at once until it is measured. Not metaphorically, literally, a particle can be here and there at the same time. This idea is hard to grasp because our brains are wired for definite outcomes. We expect that if we flip a coin, it will land on heads or tails, never. But in the quantum world, before you look, it truly exists as a blend, not just uncertain, but actually in all possible states. That blend is described by a mathematical object called a wave function. The wave function contains all the probabilities of what a system could be. It evolves smoothly according to the Schrödinger equation, a deterministic rule, but when we measure the system, the wave function collapses. The smooth blur of options snaps into one single outcome. This is not just theory, it has been shown in countless experiments. In the famous double-slit experiment, particles show an interference pattern, evidence that they are passing through both slits at once. Until you look, when observed, the particle picks one path. Superposition collapses into certainty. And it gets stranger. Particles can be in a superposition of energy levels, spin states, or even time evolutions. An electron can be spinning clockwise and counterclockwise simultaneously. A photon can be polarized vertically and horizontally at once. This leads to the idea of quantum bits, or qubits. In classical computing, a bit is either 0 or 1, but a qubit, thanks to superposition, can be 0, 1, or both at once. This allows quantum computers to explore vast combinations simultaneously. It is not faster by repetition, it is faster by parallel existence. But what does it mean to exist in two states? Is the particle really in both positions, or is it just a lack of knowledge? The answer depends on how you interpret quantum theory. Some say the particle has no defined state, until you ask. Others say all outcomes exist, but only one becomes yours. Either way, the result is the same. Superposition is not uncertainty. It is not a coin spinning in the air. It is a genuine coexistence of realities. The particle doesn't just have an unknown value, it has every value allowed by the system, all at once. And only when measured, it reveals just one. The rest vanish. This is the idea behind Schrödinger's cat, the famous thought experiment. A cat is placed in a box with a quantum mechanism that has a 50% chance of releasing poison. Until the box is opened, the system is in superposition. The cat is both alive and dead. Not in a metaphorical sense. In the framework of quantum theory, both outcomes are real, until one is observed. The cat becomes a symbol of quantum absurdity. And yet, this absurdity is real. It is the basis for quantum chemistry, superconductors, semiconductors, and the very function of your smartphone. Without superposition, transistors wouldn't behave the way they do. Atoms wouldn't form stable bonds. The modern world is built on impossibilities that became real. Even the vacuum of space is full of superpositions. Quantum fields fluctuate between all possible configurations. Particles and antiparticles appear and annihilate, not in one state, but in a sea of overlapping possibilities. The universe doesn't sit still, it shimmers with options. But how do we go from many to one? That is the mystery of measurement. When we observe a quantum system, the wave function collapses. Why? No one knows for sure. Some interpretations, like Copenhagen, say it's a fundamental feature of interaction. Others, like many worlds, say collapse never happens. We simply follow one path in a branching multiverse. There are even ideas like objective collapse theories, where the wave function collapses randomly at some threshold of mass or complexity, or pilot wave theory. Particles have definite positions guided by an invisible wave. Each model tries to explain the jump from superposition to reality, but the jump remains mysterious. What we do know is that superposition works. It makes accurate predictions, it matches experiments, and it tells us that reality at its core is not singular. It is layered, probabilistic, full of shadows that only become solid when the light of observation shines. Before that, they are possibilities, equally real, equally present. And so, in the quantum world, the phrase "it depends" becomes a fundamental law. A particle's path, energy, position, and identity all depend on how you choose to look. The universe is not fixed, it is participatory. It offers you options and waits for you to decide. Chapter 13. Decoherence. How the world forces reality to choose. In the quantum world, possibilities bloom like wildflowers. A particle isn't just somewhere, it's everywhere. It could be. The system doesn't just evolve one way, it evolves all ways, layered in superposition. But then something happens. The strange disappears. The wave function collapses. Reality makes a choice. For a long time, physicists believed this collapse came only through measurement, the conscious or mechanical act of observing a quantum system. But what counts as a measurement? Does it require a detector, a human eye, a camera? The answer, it turns out, is simpler and more unsettling. You don't need to measure a system for it to lose its quantum magic. The world itself is enough. This is the idea of quantum decoherence, a process that explains why quantum superpositions fade into classical outcomes. It doesn't require observation, it requires interaction. When a quantum system becomes entangled with its environment, its delicate state is disrupted. And what was once many possibilities becomes one. Think of a snowflake falling through still air. It spins gently, untouched. But as soon as it touches the ground, its symmetry vanishes. Contact breaks the perfection. Decoherence. is the snowflake's landing, the moment when quantum isolation gives way to environmental chaos. To stay in a superposition, the system must be isolated. No heat, no light, no vibration, no molecules brushing past. But in the real world, nothing is truly isolated. Everything is bathed in photons, in particles, in random noise. And this noise, this constant chatter of the cosmos, destroys coherence. This is why we don't see superpositions in daily life. Why chairs don't blur across rooms. Why cats don't shimmer between states. It's not because the rules are different. It's because the environment is always watching. Every breath of air, every photon of sunlight, every molecule in your body is a tiny observer. When a quantum system interacts with its surroundings, the information about its state leaks out. This leakage doesn't collapse the wave function, not exact, but it spreads the coherence so thin, so wide, that interference becomes impossible. The system is no longer pure, it's entangled with the world, and it can't be undone. Decoherence happens incredibly fast. For large systems, it can take less than a trillionth of a second. That's why macroscopic objects like baseballs or people behave classically. Their quantum possibilities are drowned in environmental noise before they have time to matter. But in highly controlled systems, we can fight decoherence. In quantum computers, for example, qubits must be kept cold, isolated, and undisturbed. Scientists use cryogenic temperatures and shielding to slow decoherence long enough to perform calculations. Every extra moment of coherence is a miracle. Decoherence doesn't explain why we see one outcome, but it explains why we don't see many. It doesn't destroy superposition, but it hides it, makes it inaccessible. The quantum wave spreads outward, entangling with trillions of particles, and in that spread, interference dies. Imagine throwing a stone into a pond. The ripples move outward, touching everything. At first, they're sharp, precise, but as they travel, they scatter, they blur, they vanish into noise. Decoherence is that scattering. A system once coherent becomes entangled with too much, and coherence disappears. This has led some to rethink the boundary between quantum and classical worlds. Perhaps there is no boundary, only degrees of entanglement. A spectrum, not a wall. In that view, the classical world is simply what the quantum world looks like when it's entangled beyond rescue. It also suggests that measurement doesn't cause collapse. It just marks a point where decoherence has already done its work. By the time you observe a particle, it's already tied to countless unseen interactions. Your measurement is the last thread, not the first. The wave function didn't die. It spread too far to see. And still, we don't fully understand what happens at that final moment. Decoherence tells us how superpositions become unobservable, but it doesn't tell us why we see only one result. That question remains open. The boundary between math and mind, between system and self. But what decoherence does tell us is that quantum behavior is not fragile because it's broken. It's fragile because the world is noisy. The universe is always listening, always touching, always tugging at the seams of superposition. It forces choice by contact. Reality becomes real through entanglement. And yet, in the shadows, superposition persists. In shielded labs, in superconducting circuits, in the cold dark of interstellar space. Wherever noise fades, the quantum hum returns, and reality remembers how to dance. Chapter 14. The Observer Effect. Does consciousness collapse reality? The moment we observe, something changes. In the quantum world, this is not metaphor, it is law. A particle in superposition becomes definite. The probability cloud becomes a single point. The act of looking does more than reveal reality. It helps create it. This idea, known as the observer effect, has sparked decades of confusion, debate, and philosophy. What does it mean to observe? Is it enough to have a machine take a measurement, or does it require something more, a conscious mind, an act of awareness? Does consciousness collapse the wave function? Let's begin with what physics tells us. In the standard interpretation of quantum mechanics, the wave function evolves smoothly until an interaction occurs. That interaction, with a detector, an environment, a measuring device, causes the system to decohere, to superposition disappear. But this leaves a hole. What makes an interaction a measurement? When exactly does the wave function collapse? If a detector registers a result, but no one looks at the screen. Has reality still been resolved? Or is it waiting for a conscious mind to arrive? This question haunted early quantum physicists. Niels Bohr insisted that classical measurement devices were needed to interpret quantum systems, that we must describe the world in terms we can observe, but he avoided saying whether consciousness played a special role. He left the boundary fuzzy. Others were more provocative. John von Neumann argued that the measurement chain, from particle to detector to screen to eye, must end somewhere, and that it ends in consciousness. In his view, the observer's mind collapses the wave function. This view gained support from physicists like Eugene Wigner, who famously asked, "If consciousness is not involved, how does the collapse happen?" He imagined a version of Schrödinger's cat where a friend checks the box, and then asks, "Does the cat exist before you know what your friend saw? Does your awareness complete the event?" The idea is both seductive and unsettling. It makes the mind seem central to physics, not just a passive witness to the universe, but an active participant in its unfolding. Reality, in this view, is not fully real until someone observes it. But modern interpretations push back. Most physicists today argue that consciousness is not necessary for collapse. They point to decoherence, to environment-induced superposition decay, to the idea that measurement is just entanglement with a larger system. The mind is not required. In these views, what we call collapse is really information leakage. The wave function becomes so entangled with the environment that interference disappears. No subjective experience is needed. The world makes choices on its own. Consciousness is not a cosmic referee, just another system. And yet, the mystery persists. Because when we try to describe what is, we can't escape the role of what is observed. In quantum theory, we calculate probabilities, not facts, and those probabilities only resolve when a result becomes known. Known to whom? Some physicists embrace this question directly. In Cubism, quantum Bayesianism, the wave function is not a property of the system, but a tool for an observer to manage their expectations. Measurement is personal. Reality is updated when beliefs are updated. The observer is central, not because they collapse reality, but because they define it. Others return to consciousness from a different angle. They ask, what is awareness, if not a kind of measurement? If consciousness arises from quantum processes in the brain, if thought is entangled, then could our very minds be quantum systems? Could perception itself ride the same wave as a photon? This is speculative. We do not have a theory of consciousness. We do not know whether it is classical or quantum. But the question remains, why does the universe, governed by probabilities, appear so definite to us? One possibility is that we too are part of the equation. That observation is not something we do to the world, but something we do with it. That perception is not outside the system, but embedded in it. That the act of knowing is a quantum act. Another possibility is simpler, that reality is always definite, and the wave function is just a mathematical tool. That collapse is not physical, but a change in knowledge. That there is no mystery, just a misunderstanding of what we mean by real. But if that were true, why does the math resist such an interpretation? In the end, the observer effect is not just about quantum physics. It is about the relationship between mind and matter, between what is seen and who, between probability and experience. We may never find a final answer, but the question itself reshapes how we view the universe. It reminds us that the line between object and observer is not that every glance, every measurement, every thought is part of the story, that reality is not only what is out there, it is also what rises to meet our attention. Chapter 15. The vacuum is not empty. Welcome to the quantum sea. We imagine emptiness as the absence of everything. A blank slate. A quiet room. A place where nothing moves. Nothing stirs. Nothing exists. In classical physics, this was called the vacuum. A space devoid of matter, fields, and force. But in the quantum world, emptiness is an illusion. The quantum vacuum is not silent. It is not still. It is not empty. It is a restless sea of activity, a bubbling, shifting ocean of potential. Particles emerge and vanish. Fields fluctuate. Energy appears, disappears, and reappears again. This is not poetic language. It is reality. Even in the coldest regions of space, where temperatures approach absolute zero and all particles are gone, the vacuum remains active. This activity is not a flaw. It is built into the rules of quantum field theory. It cannot be switched off. Every point in space contains a quantum field. These fields are not things we place into space, they are space. The electromagnetic field, the electron field, the quark field, all of them permeate the universe, even where nothing else is present, and these fields never lie flat. Due to the uncertainty principle, the energy of a quantum system can never be exactly zero. There is always fluctuation, always motion, always a residual vibration, even in the ground state. This is called zero-point energy. The vacuum has a flaw, and it hums. From this restless hum, virtual particles are born. They are not like the particles we know, not electrons or photons that persist in time. They exist briefly, borrowing energy from the vacuum, then vanishing before they can be fully seen. They are allowed by uncertainty, and forbidden from permanence. And yet, they leave traces. These vacuum fluctuations affect real physics. They contribute to the Lamb shift, a tiny change in electron energy levels inside atoms. They explain the Casimir effect, where two metal plates in a vacuum feel a gentle force pulling them together. The vacuum creates pressure. The vacuum even affects the speed of light. In quantum electrodynamics, photons constantly interact with the sea of virtual particles. These interactions subtly alter how light moves, bends, and scatters. The vacuum is not a stage, it is a participant. In fact, the vacuum may be the most fundamental thing there is. Every particle we know, every electron, proton, quark, is an excitation of an underlying field, and those fields are always present, even when no particles appear. What we call empty space is actually a field-rich medium. Think of a violin string. Even when not plucked, the string is there, full of tension and potential. The vacuum is that string, particles are the notes, but the music never truly stops. String always quivers, softly, beneath silence. Some theories even suggest that the entire universe emerged from a vacuum fluctuation, a brief, spontaneous distortion in the fabric of space-time that inflated, expanded, and cooled into the cosmos we now inhabit. If this is true, then everything, stars, galaxies, people, arose from what we once called nothing. But that nothing was never truly empty. The vacuum may also hold clues to the dark energy driving the expansion of the universe. Quantum field theory predicts a vast vacuum energy, much greater than what we observe. Why the numbers don't match remains one of the greatest puzzles in science. But it reminds us that emptiness is not simple. And in particle physics, the vacuum is not uniform. Fields like the Higgs field have non-zero values even in the vacuum. This field gives particles mass by interacting with them constantly, even in empty space. Your weight depends on the nature of the vacuum. We once believed that space was passive, that it did nothing, that it simply held things. Now we know space is active, structured, and rich with hidden movement. A medium, not a void, a fabric that shapes and responds. A living background. Even time is affected by vacuum behavior. In some interpretations of quantum gravity, space and time emerge from entanglement patterns in the vacuum state. In this view, reality is built from relationships, not points. The vacuum is not a place, it is a process, and yet it's invisible. You cannot touch it, see it, or feel it directly. You sit in a room surrounded by what seems like nothing, but in that space, particles flicker in and out of being. Fields interact, forces pass through. You are never alone. So what does this mean for how we see the world? It means that silence is never silent, that stillness is an illusion, that the void is full of meaning. The most important structures may not be what's present, but what supports what's present. The unseen scaffolding beneath it all. And if the vacuum is never truly empty, then what else do we misunderstand? What other nothingness holds power we cannot see? The answers may lie in the fabric of space itself, not as emptiness, but as an intricate weave of energy, law, and form. The sea beneath the surface. Chapter 16. Black Holes. When gravity rips the rules apart, there is a place in the universe where gravity becomes so strong that nothing can escape. Not light, not time, not even the laws we thought were unbreakable. That place is a black hole. And when we try to understand what happens there, the universe stops making sense. Or rather, it begins to speak in a language we no longer recognize. Black holes are not monsters. They are not holes. They are regions of warped space-time, pockets, where gravity has pulled everything so tightly inward that even light cannot climb back out. They are the final stage of collapse. A body dies, and in doing so, tears a hole in the map of space. a point from which no path returns. They begin with a star. When a massive star exhausts its fuel, it can no longer resist its own weight. The balance between outward pressure and inward gravity breaks. The core collapses, the atoms are crushed, the electrons and protons are forced into neutrons. And if the mass is great enough, even the neutrons cannot hold. The collapse continues, past every known resistance, down into an abyss. What remains is a singularity, a point of infinite density, where the known laws of physics no longer apply. Around it forms an event horizon, the surface beyond which nothing can escape. Cross that boundary, and you are gone. But what happens at the singularity? Don't know. Our equations break down. General relativity, Einstein's magnificent theory of gravity, predicts infinite curvature, but quantum mechanics cannot handle infinities. This is the first way black holes break our common sense. They force us to confront the limits of our theories. Gravity and quantum mechanics are the two pillars of modern physics, and inside a black hole, they collide. You do not yet know how to unify them. And yet, black holes are not rare. They are not exotic exceptions. They are everywhere, at the hearts of galaxies, drifting through space, even possibly hidden in the early moments of the cosmos. One lurks at the center of our Milky Way. Its mass is millions of times greater than our sun. When we observe stars near that black hole, we see them whip around an invisible center, obeying gravity's pull but revealing no source of light. Their orbits are precise. Their silence is deafening. Something is there, something dark, massive and irresistible. A black hole. The second way black holes challenge us is with time. According to general relativity, time slows down near a massive object. The stronger the gravity, the slower time flows. Near a black hole, this effect becomes extreme. To an outside observer, someone falling into a black hole would appear to freeze at the edge, moving slower and slower, never quite crossing. But to the falling person, time continues as normal. They pass the horizon, they fall inward, they reach the singularity in finite time. Reality diverges based on where you stand. This leads to paradoxes. From the outside, nothing escapes, but from the inside, time ends. Two descriptions of one object, both valid, both incompatible, a puzzle not yet solved. The third way black holes break physics is through information. In the 1970s, Stephen Hawking discovered that black holes are not entirely black. Due to quantum effects near the event horizon, they emit a faint glow, now called Hawking radiation. This radiation allows black holes to lose mass and eventually evaporate. But here's the problem. What happens to the information that fell in? According to quantum mechanics, information can never be destroyed. It can change form, but it must be preserved. But Hawking's calculation suggested that when a black hole evaporates, the information is lost. This is the black hole information paradox. Decades of work have gone into solving it. Some believe information is encoded in the Hawking radiation in subtle correlations we have yet to decipher. Others believe it is stored on the event horizon itself, a two-dimensional surface encoding three-dimensional data. This is the holographic principle. The idea is radical, that the information content of a region of space can be described entirely by a theory on its boundary. In this view, the universe itself may be a hologram, with what we perceive as volume actually encoded on a surface. Space is not what it seems, and black holes may be the key to unlocking it. We have now seen the outlines of black holes, through gravitational waves, through orbits, and most recently, through images. In 2019, the Event Horizon Telescope captured the shadow of a black hole, the outline of the void, surrounded by glowing plasma. It confirmed Einstein's predictions, and reminded us of how much we still don't know. We had seen the unseen. Black holes are not just objects, they are portals into deeper questions. They teach us about entropy, about time, about the fabric of the cosmos. They are where our best theories go to break, and through that break, new understanding must come. So, what lies beyond the event horizon? Is it a singularity, a bridge to another universe, a remnant encoded in surface entropy? We do not know. We only know that physics itself begins to whisper in unfamiliar tones. And so, when we gaze into the darkness of a black hole, we are not staring into absence. We are looking at a mirror, one that reflects the limits of our knowledge and dares us to go further, to face a reality where time bends, information stretches, and gravity tears the map of space. Chapter 17. The Cosmic Ballet. How orbits carve harmony into space. Gravity is usually associated with falling, with the apple, the weight, the pull. But in the heavens, gravity does something different. It does not crash or tumble. It curves. It dances. And in that dance, the universe finds rhythm. When Isaac Newton watched an apple fall from a tree, he imagined the same force reaching far beyond the orchard. He asked, if gravity pulls the apple to Earth, could it also pull the moon into orbit? Could the planets be falling, not down, but around? The answer was yes. An orbit is not a circle, not exactly. It is a path of compromise, a constant balance between motion and pull. A satellite wants to move forward, gravity wants to pull it inward. The result is neither collapse nor escape, but endless falling sideways. Imagine firing a cannon from the top of a mountain. At a low speed, the ball arcs and falls. At a higher speed, it flies farther. But if you could fire it fast enough, just right, the curve of its fall would match the curvature of Earth. It would fall forever, never landing. This is an orbit, not a fixed circle, but a self-sustaining fall. The Earth orbits the Sun this way. The Moon orbits us. Every object in space that loops around another is engaged in this quiet tension, motion versus gravity, and through it, order emerges. Johannes Kepler, long before Newton described how planets move, he found that they trace ellipses, not perfect circles, with the Sun at one focus. Their speed changes depending on distance. Closer means faster, farther means slower. Kepler's laws were born from observation. Newton's law of universal gravitation gave them reason, and Einstein would later refine that reason, showing that objects move not because of a force pulling across space, but because space itself is curved. An orbit, then, is a body following the straightest path in a bent geometry, a geodesic in space-time. But even in Newton's view, orbits revealed beauty. His law, that gravity decreases with the square of the distance, allowed planets, moons and satellites to glide through space with predictable grace. And this grace, this predictability, is not limited to planets. It applies to atoms too. The hydrogen atom, for instance, has an electron orbiting its proton. Though not in classical orbits, the quantum energy levels mirror orbital harmony. Discrete, stable configurations, probabilistic shells, tiny echoes of celestial motion. This shared structure between the cosmos and the atom suggests a deep unity, that the same principles govern the large and the small, that gravity, or its analogues, etch curves into the fabric of existence, and in those curves we find form. Even chaotic systems like asteroid belts or planetary rings show resonance. Moons influence each other, orbital periods align, tugs and nudges synchronize. Over time, disorder gives way to patterns, cycles, symmetries, and rhythms. Gravity doesn't just pull, it composes. And this harmony is not just mechanical, it is foundational. Orbits conserve energy. They conserve momentum. They define boundaries of influence, the Hill sphere, where a body's gravity dominates. They set the stage for tides, eclipses, and seasons. They make time itself measurable. Without orbits, there is no calendar, no moonlight, no stability for life. The Earth's path around the Sun, and the Moon's path around us, regulate temperature, light, and the conditions for evolution. These paths are not random. They are carved by gravity into sustainable loops, a cosmic choreography that made existence possible. Even in chaos, orbit-like behaviors appear. Galactic arms. Stars swirl in patterns shaped by mass and motion. In protoplanetary disks, dust coalesces into spirals, into rocks, into worlds. Orbits don't just preserve structure, they build it. And yet, orbits are fragile. A tiny nudge can destabilize them. A gravitational encounter with a passing star, a resonance with another planet. These perturbations can stretch orbits, flip them, or fling objects into interstellar space. Harmony, while beautiful, is not permanent. We see this in the story of Mercury. Its orbit precesses slightly, a tiny drift unexplained by Newtonian gravity. Einstein's general relativity resolved the mystery. The Sun's immense mass bends space-time just enough to alter Mercury's path. A reminder that even the most precise models yield deeper truths. And then there are rogue planets, worlds ejected from their orbits by violent encounters. They drift through space alone, no longer bound by any star. They are orbitless, homeless, yet still shaped by the rules of motion that once held them, the darker side of the ballet. Still, for every lost planet, there are countless stable ones, and their presence reminds us that the universe, for all its chaos, builds enduring patterns, not by freezing motion, but by curving it into art. Every orbit is a signature, a conversation between body and gravity. And so we look upward, not just to marvel, but to understand. We map the heavens, we launch satellites, we calculate slingshots around planets. We live in a time where the cosmic ballet is not just observed, it is choreographed. The laws of motion, once abstract, have become our tools. Chapter 18. The Standard Model. The blueprint beneath reality. To understand the universe, we must first ask a deceptively simple question. What is everything made of? Not in a poetic sense, but in the language of physics, the language of building blocks. The answer is known as the Standard Model of particle physics. It is a theory, yes, but it is also the most precise, predictive, and experimentally confirmed model in the history of science. It does not explain everything, but what it does explain, it explains with breathtaking accuracy. At its core, the Standard Model describes three of the four known fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force. Gravity, strangely, is absent. We'll return to that mystery later. The model begins with particles, 12 fundamental matter particles, grouped into two families, 6 quarks and 6 leptons. These are the ingredients of everything we touch, see and breathe. The up and down quarks form protons and neutrons. Electrons, a type of lepton, orbit atomic nuclei. Quarks come in pairs, up-down, charm strange, top-bottom. Leptons also come in pairs. Electron and electron neutrino, muon and muon neutrino, tau and tau neutrino. Each has a corresponding antiparticle. These are not concepts. They are real, detected in particle accelerators, seen in cosmic rays. But particles do not act alone. They interact, and these interactions are carried by force carriers, also known as gauge bosons. Photons carry electromagnetism, gluons carry the strong force, Wadum and Z bosons carry the weak force. These particles mediate every interaction among matter. If two electrons repel each other, it is because they exchange a photon, not the kind you see as light, but a virtual photon that carries force. If quarks are bound into protons, it is because they exchange gluons, constantly, rapidly, in a chaotic web. If a neutron decays, it does so by emitting a W boson, transforming a down quark into an up quark. And then there's the Higgs boson, the particle discovered in 2012 at CERN. It is unlike the others. It does not carry a force. Instead, it interacts with other particles to give them mass. The Higgs field fills the universe. Particles acquire mass by moving through it. Without it, everything would remain massless, zipping through space at the speed of light. This framework of particles and forces is not a human invention. It is a discovery. It is the result of decades of experiments, collisions, detections, anomalies, and confirmation. The Standard Model predicted particles long before they were found. It describes processes with astonishing precision, and yet it feels incomplete, because something strange happens when you zoom out. The Standard Model, for all its success, leaves enormous gaps. It does not include gravity. It does not explain dark matter. It does not account for dark energy. It cannot explain the neutrino masses, which we now know are not zero. It also fails to answer deeper philosophical questions. Why these particles? Why these masses? Why 3 generations? The Standard Model contains over 24 free parameters, constants that must be input by hand. It works, but it doesn't explain why it works. And yet, it holds. Every collider experiment, from Fermilab to the Large Hadron Collider, has confirmed its predictions again and again. Scattering angles, decay probabilities, energy distributions all fall within its scope. It is a machine of precision, but it is also delicate. The Higgs boson, for example, sits at a very particular mass, about 225 gigaelectron volts. If it were heavier or lighter, the universe could be radically different. Its mass appears finely tuned, a coincidence that has sparked theories of deeper structure. One such idea is supersymmetry, a proposed extension of the Standard Model that doubles the particle list, assigning each known particle a heavier partner. These superpartners would help stabilize the Higgs mass, and could explain dark matter, but so far we have found no evidence of them. Another idea is string theory, which suggests that all particles are tiny vibrating strings, their properties determined by frequency and mode. In this view, the Standard Model is just one vibration among many, a low-energy echo of a higher dimensional reality, but string theory remains untested. Then there is the Grand Unified Theory, the dream of merging the electromagnetic weak and strong forces into a single interaction at high energy. The math allows it, the physics suggests it, but the unification scale is far beyond what we can probe. The Standard Model stops just short of that mountaintop. And still, we use it. We build colliders based on it. We write simulations. We send satellites. The global positioning system relies on corrections predicted by relativity and quantum electrodynamics. Our electronics depend on the Standard Model. It is woven into modern life, invisible, but everywhere. Some physicists call it ugly, too many parts, too many assumptions. Others call it beautiful, elegant in function if not form. But everyone agrees it works, and in its precision, it leaves us restless, because nature rarely builds a house with no foundation beneath. Perhaps the Standard Model is just the visible floor of a much deeper structure, one we cannot yet see, a lattice of symmetry of fields of forms we haven't imagined, or perhaps it is the final blueprint, nature's finished design, forever subtle and strange. We do not yet know. But when we look at the periodic table, at molecules, at stars and bones and clouds, we are seeing the Standard Model at work, in the interactions of gluons, in the flex of electrons, in the presence of mass. It is the code beneath appearance, the script behind the stage. Chapter 19. Dividing by Zero. The forbidden operation that breaks space-time. There are few rules in mathematics more universally feared, more instantly rejected than this. You cannot divide by zero. It is not a suggestion. It is a commandment. From the earliest lessons in school we are told that dividing any number by zero is undefined. It breaks the rules. It leads to contradiction. But what does that really mean? Why does this simple action, a division, ripple so destructively through both math and physics? To begin, recall the meaning of division. 12 divided by 3 means, how many times does 3 fit into 12? The answer is 4. But 0 fits into no number any number of times, or, looked at differently, it fits into any number an infinite number of times. This ambiguity is the problem. If you try to divide 1 by 0, what are you asking? How many times does 0 fit into 1? Infinitely many? Or none at all? The answer is not well defined. It doesn't settle, and in mathematics, undefined operations spread instability like cracks in a foundation. When you attempt to divide by 0, the result grows without bounds. In calculus, this manifests as a singularity, a point where a function shoots to infinity or becomes discontinuous. It creates asymptotes, edges, breaks in space. It's like asking for the volume of an infinitely small container. This problem isn't just theoretical. In physics, division by 0 shows up in the most extreme situations, like black hole singularities, where density becomes infinite, or in the early universe where the size of space compresses toward 0. The mathematics explodes, the equations tear. In Einstein's general relativity, the curvature of space-time is described by equations that include terms involving division by distance, and when that distance goes to 0, the curvature becomes infinite. Gravity breaks the map. These are not mistakes. They are clues. A singularity in physics is more than just a number going to infinity. It represents a place where our physical laws can no longer predict what happens. Causality breaks down. Space-time stops being smooth. The future becomes unknowable. And all of this starts, mathematically, with a division by 0, a denominator that vanishes, a point where the fabric of the equation snaps. When this happens in physical models, it tells us our theory has reached its limit. But can we go further? Can we make sense of dividing by 0, or at least understand it in a deeper way? Some mathematicians have explored projective arithmetic, where division by 0 is reimagined in extended number systems. Others use limits, approaching 0 from either side. In calculus, we define behavior near 0 using limits. We never actually divide by 0. We divide by a number that approaches 0, like 1 over epsilon. This gives rise to derivatives, slopes, rates of change. and it is how we handle infinities in real analysis. Yet, even limits are cautious. If the limit from the left and right don't agree, we say the limit does not exist. We refuse to patch over contradiction. Math insists on clarity. No assumptions. Zero is not a ghost to be tamed, it is a boundary to be respected. In physics, however, nature sometimes whispers through the cracks. A division by zero might signal the need for a new theory. When the equations of general relativity yield infinities, we look toward quantum gravity. When electric fields diverge at a point charge, we suspect deeper structure. And in string theory, particles are not point-like, but extended, tiny loops. This removes the singularity. Division by zero never occurs because the zero is replaced by something with size. No infinite spikes, no sharp corners, just smooth, continuous geometry. In this way, division by zero becomes a signpost. It marks the edge of knowledge, the boundary where one framework fails and another must begin. It's not a bug, it's a warning. The language you are using can go no further. So when space-time becomes infinitely curved at the core of a black hole, it's not necessarily a place that exists. It is a flag, a cry from the equations. You have passed beyond what this map can explain. Build a better one. Even in thermodynamics, division by zero appears when we try to cool something to absolute zero. The entropy, or disorder, resists this. The energy required to extract heat becomes infinite. Absolute zero is forbidden not by hardware, but by math. We also see this in Zeno's paradoxes, philosophical puzzles where distance is halved infinitely. You never reach your destination. You divide and divide and divide. But physics, through calculus, answers this with convergence. You approach zero, but you never divide by it. So what does it all mean? Why does such a simple number, nothing, have such power? Because zero is not absence, it is precision. It is the threshold where our models become brittle, where reality refuses to be boxed into categories we find comfortable. And so, in the classroom we write undefined next to division by zero. But in the lab, in the telescope, in the equations of stars and voids, division by zero becomes a deeper truth, a red line, a flare, a whisper that says, the world is stranger than this. Chapter 20. The shape of space. From curved universes to impossible geometries, what shape is the universe? It's a simple question, and yet the more you think about it, the more it slips through your fingers. Because space is not just an empty stage where matter performs. Space itself has structure, a shape, a texture, a geometry. And that geometry bends everything we thought we understood. For centuries, the dominant belief was that space was flat, that the three dimensions of length, width, and height extended infinitely in all directions, straight, uncurved, neutral. This is Euclidean space, the geometry of schoolbooks and blueprints. In Euclidean geometry, parallel lines never meet. The angles of a triangle always add up to 80 degrees. Circles behave predictably. Distance is a matter of rulers and straight paths. But what if the universe is not flat? What if space is curved, warped by mass, energy, or its own topology? Einstein's theory of general relativity opened that door. Space is not static. It bends in response to matter. The sun doesn't pull the Earth. Instead, it curves space-time and Earth follows the curve. The geometry of the cosmos is dynamic. This means that the universe can take on multiple possible shapes. Not just flat, but positively curved like a sphere, or negatively curved like a saddle. In a positively curved universe, space loops back on itself. Travel far enough in one direction, and you return to where you started. There are no edges, no borders, just wrap around. In a negatively curved universe, space spreads out, open, infinite, expanding faster than you expect. Triangles have angles that add up to less than 80 degrees. Parallel lines diverge. Distances grow exponentially. Light rays bend outward. Cosmologists today use data from the cosmic microwave background, the oldest light in the universe, to measure the shape of space on the largest scales. The current evidence suggests the universe is very nearly flat, but nearly is not the same as perfectly. A slight curvature, spread across billions of light years, could change everything. And then there's topology, the study of how space is connected. Topology asks, can space be looped, twisted, compacted, without necessarily being curved? Could the universe be shaped like a torus, a donut, where paths wrap around both horizontally and vertically? In such a universe, you could see the back of your own head, given enough time and distance. Light would travel around space and return to its origin. Galaxies could appear multiple times in different locations, like a cosmic hall of mirrors. This isn't science fiction, it's a real mathematical possibility. There are even stranger geometries, like manifolds with multiple dimensions curled up tightly, invisible to us. String theory, for example, requires 6 or 7 extra dimensions beyond the 3 we see. These dimensions are thought to be compactified, rolled up in shapes called Calabi-Yau manifolds. They affect physics, even though we cannot perceive them directly. To us, space appears 3-dimensional, but that's an observation, not a law. Higher dimensional spaces, known as hyperspaces, are consistent with both math and theory. We just lack the tools to visualize them. Our minds evolved in a 3-dimensional world, but nature may be richer than our senses. Even time can be seen as a dimension. In space-time, the universe becomes a 4-dimensional block, past, present, and future all existing at once. In this view, motion is just a path through the block. Space and time are not separate, but woven together. And when space-time curves sharply near a black hole or the Big Bang, the shape of space changes radically. Near a singularity, distances shrink, directions twist, and paths collapse. The geometry becomes extreme, unfamiliar, perhaps even non-Euclidean. Non-Euclidean geometry is not an abstraction. It's the real shape of space near intense gravity. Imagine a triangle drawn on the surface of a sphere. Its angles add up to more than 180 degrees. Space is telling you that it's curved, not flat. This is how gravity reveals itself, not as a pull, but as a change in geometry. This also affects the path of light. In curved space, light no longer travels in straight lines, it bends. This leads to gravitational lensing, where distant galaxies appear distorted, duplicated, or magnified as their light bends around intervening mass. Space behaves like a lens. Invisible, yet powerful. Even emptiness is not neutral. Quantum fluctuations give rise to energy, pressure, curvature, even in the vacuum. This can curve space subtly, like a canvas stretched under tension. It may be how dark energy, the mysterious force accelerating cosmic expansion, manifests in the geometry of space itself. So what is the shape of space? The answer depends on scale, on content, on the interplay between geometry and energy. On small scales it may be nearly flat, on large scales it may curve, twist, or repeat. On quantum scales it may flicker and foam. Some physicists even speculate that space is not continuous at all, but quantized, made of discrete units like atoms. This is the idea behind loop quantum gravity, where the fabric of space consists of tiny loops. Geometry becomes granular. Smoothness is an illusion. At this frontier, geometry becomes fluid, capable of tearing, reconnecting, or shifting entirely. This opens the door to concepts like wormholes, where space folds back on itself to create shortcuts, or closed time-like curves which allow for loops in time. These are not confirmed, but they are mathematically valid in some solutions of general relativity. So we return to the question, what shape is the universe? The answer is not singular, it is layered. On some scales it is flat, on others curved. At extremes, perhaps discrete or topologically knotted. The universe may not have one shape, but many. And every discovery we make reshapes not just space but our minds. Geometry is not background, it is character. It molds motion, time, matter, and light. It is the silent partner in every physical law. It holds the universe together. Chapter 21. Something from Nothing. The ultimate question of existence. Why is there something rather than nothing? Is not just a question for philosophers, but one that haunts physicists, cosmologists, and anyone who has ever stared into the night sky and wondered, why does anything exist at all? Why is there a universe filled with matter, energy, space, and time, instead of an empty void with no laws, no particles, no structure? To even begin to approach this question, we must first ask, what do we mean by nothing? In physics, nothing is rarely absolute. The closest we come to true nothing is the quantum vacuum, a state with no particles, no radiation, no matter, and yet it is not empty. The vacuum is alive. It teems with virtual particles, constantly appearing and vanishing. Fluctuations bubble up from this sea of uncertainty. Particles pop into existence, only to disappear again. borrowing energy from the vacuum and paying it back almost instantly. This quantum nothingness is not silence, it is a background hum, a zero-point energy that cannot be removed. Even in perfect emptiness there is still structure, still law, still potential. Could the universe have emerged from such a vacuum? Some theories say yes. According to quantum cosmology, space and time themselves may have spontaneously arisen from a quantum fluctuation. Just as a particle can pop into being, so might an entire cosmos. Stephen Hawking and James Hartle proposed the no-boundary proposal, suggesting that the universe has no edge in time, no beginning point in the traditional sense. Time may have simply become time from a timeless state. The universe could tunnel into existence the way particles tunnel through energy barriers in quantum mechanics. Other models suggest the universe is the result of a quantum vacuum decay, a transformation from one vacuum state to another. In this view, the Big Bang was not the start of everything, but a shift, a phase transition in the fabric of reality. Space expanded, matter congealed, time began ticking. But even this leaves deeper questions. If the universe came from a vacuum, where did the vacuum come from? If the laws of physics allowed the universe to arise, where did those laws come from? Are the laws themselves eternal or emergent? Some physicists propose that the laws of physics are statistical, that among many possible configurations, the one we observe is simply the one that happened to allow complexity, observers and time. This leads to the concept of a multiverse, an ensemble of universes each with different laws. We exist in the one where something happened, because it could. But others resist this. The multiverse, they argue, doesn't explain existence. It multiplies it. Why should there be a multiverse at all, rather than nothing? Why should possibility exist? Here we enter a realm where physics meets philosophy. Some thinkers argue that nothingness is unstable, that nothing is not the default state but a special case requiring constraint. In other words, something is more natural than nothing. Others turn to mathematics, suggesting that mathematical structures exist timelessly, and the universe is simply one such structure realized in physical form. If math exists necessarily, and if math can describe a universe, then perhaps existence is inevitable, a kind of mathematical Platonism. Still others invoke the anthropic principle, the idea that we can only ask the question in a universe where the answer is yes. If universes without something cannot support life, then the question only arises where something exists. But this feels unsatisfying. It explains the where, but not the why. And so we come to a possibility that cannot be proven, but must be faced. Perhaps there is no reason. Perhaps the universe exists because it can, not for a purpose, not for a goal, but because the laws, or the pre-laws of nature, allow, and once allowed it was bound to happen. In this view, nothing is not the most natural state, it is a possibility among many, and something is not a surprise, it is a realization of potential, a drop in the quantum ocean expanding, cooling, forming stars, galaxies, life, minds, and finally questions. And perhaps in the end, the question, why is there something rather than nothing, is not a question physics can answer. And perhaps it is a mirror, one that reflects the limits of our language. We ask why, assuming intent, but nature may not deal in reasons, it may deal only in outcomes. And yet, this does not cheapen the question, it deepens it, because in seeking an answer we reveal the depth of our own curiosity, our desire not just to how, but to understand meaning. Physics gives us mechanisms, but wonder gives us the courage to ask what they mean. And so the universe, this universe, remains something, not nothing. Stars burn, atoms dance, time flows, minds wonder. Perhaps that is answer enough. Perhaps the existence of the question is the most profound fact of all. Chapter 22. The double-slit mystery. How observation rewrites reality. It begins with something simple, a beam of particles, a screen with two slits, and a wall to detect the results. A straightforward setup, one that should offer predictable outcomes, but instead it offers one of the greatest mysteries in all of science. This is the double-slit experiment, and it does something astonishing. It shows us that particles, things like electrons and photons, do not always behave like particles. They sometimes act like waves, and more disturbingly, they seem to change behavior depending on whether or not they are observed. Imagine shooting small balls through a single slit. You would expect them to form a pattern behind the slit, a narrow column of impacts. Now imagine two slits. You'd expect to see two such columns. Simple, predictable, intuitive. That is the particle view. But when we send photons, particles of light, through two slits, we do not see two columns. We see an interference pattern, alternating bands of light and dark, the kind of pattern waves make, as if the photon passed through both slits at once, interfering with itself. This suggests that each particle is not just a point, but a wave function, a spread-out probability of where it might be, and when no one is looking, that wave explores every possible path. It goes through slit 1, it goes through slit 2, it goes through both, it goes through neither. All possibilities exist, until measurement collapses them. Now here is the twist. If we place detectors at the slits to observe which one the photon goes through, the interference pattern disappears. The particle chooses a path, the wave collapses. It no longer behaves like a wave, it becomes a particle again. This is not it is not illusion, it has been repeated thousands of times, with electrons, atoms, even molecules. Every time, the result is the same. The act of measurement alters the outcome. Reality shifts under the pressure of observation. This is the heart of quantum mechanics, a world where particles are described not by certainty, but by probabilities. Until we observe, we only know what might happen. And observation forces a choice. The mathematical tool we use is called the wave function, a complex valued function that encodes the possible states of a system. When not observed, a photon exists in a superposition, all paths at once. When measured, the wave function collapses, leaving a single outcome. But this raises deep questions. What counts as observation? Is it conscious awareness, a camera, the photon bouncing off a detector? At what point does potential become reality? No one fully agrees. Some interpretations, like the Copenhagen interpretation, claim that measurement is fundamental, that nature is indeterminate until observed. Others, like the many worlds interpretation, suggest that all outcomes occur, but in separate branching universes. Observation merely splits the path we follow. There are also hidden variable theories like Bohmian mechanics, which say particles always have definite positions but are guided by a pilot wave. In this view, the weirdness is not in the particle, but in the pilot, an invisible force that governs motion. These interpretations agree with experiment, but they disagree on meaning. And perhaps that is the strangest part. Quantum mechanics is the most successful theory in the history of physics. It predicts results with unimaginable precision, but no one can fully agree on what it means. The double-slit experiment is not just a curiosity, it is a window into the deepest nature of existence. It shows us that reality is not made of solid building blocks, but of probabilities, interference, and potential. That the line between what is and what could be is thinner than we thought. And perhaps most unsettling, it suggests that the act of looking is not passive, it is participatory. That reality, at least at the smallest scales, waits to be asked a question, and only then decides on an answer. That the observer is not separate from the system. The observer is part of the equation. Chapter 23: Quantum Entanglement. When reality breaks locality, there are few ideas in all of physics more counterintuitive, more deeply unsettling, and more beautifully confirmed than this. Two particles can become entangled, such that the state of one depends on the state of the other, no matter how far apart they are. It is called quantum entanglement, and it breaks every classical rule you thought reality obeyed. In everyday life, objects are separate. If you move one, it doesn't instantly affect another across the room. Information takes time to travel, forces have range, signals must move through space, but entanglement defies that logic. Start with a pair of particles, let's say electrons. If they interact in just the right way, their quantum states become linked. You measure one, and the other immediately reflects a complementary result, even if it is light years away. It is as though the universe skipped the middle. This isn't a metaphor, it's not mysticism. It is what the mathematics says. It is what the experiments confirm. And it violates one of the bedrock assumptions of classical physics, locality. The idea that objects are only influenced by their immediate surroundings. Einstein famously called it spooky action at a distance. He believed there must be hidden variables, some unseen information carried by each particle to ensure they always correlate. But this view was tested, and tested again, in experiments designed to reveal whether local realism could survive. The most famous of these are the Bell test experiments. Based on a theorem by physicist John Bell, Bell derived mathematical inequalities that any local hidden variable theory must satisfy. Quantum mechanics predicts violations of these inequalities, and the data agrees repeatedly, reliably, precisely. What does this mean? It means either particles influence each other faster than light, or measurement outcomes are not locally determined, or reality is not fully real until it is observed. None of these options are comforting. Entanglement does not allow faster-than-light communication. That would break causality, but it does allow correlation, perfect coordinated outcomes across arbitrary distances, with no signal sent. It's not communication, it's coordination, instantaneous, inexplicable. In quantum terms, the particles exist in a superposition of states. Only when one is measured does it snap into a specific outcome, and so does its twin. The choice is not made locally. It is made non-locally, by the entangled system as a whole. One way to visualize it is this. Imagine two spinning coins that are somehow connected. Flip them on opposite sides of the galaxy, and the moment you check one, the other stops spinning and shows the matching face. You didn't send a message, the system just was connected. Now scale that up. Entanglement is not rare, it happens in labs every day. It is used in quantum computing, quantum cryptography, even theoretical teleportation. It is not just a curiosity, it is a foundation. In quantum computing, entangled qubits allow parallelism, the ability to explore many computational paths at once. This is what gives quantum computers their astonishing potential. Entanglement is not a bug, it is a feature, and an essential one. In quantum cryptography, entanglement ensures secure communication. Any eavesdropper trying to measure the particles will disturb their state, revealing their presence. Entanglement becomes a shield, a guardian of secrecy. And yet, for all its usefulness, we still struggle to say what entanglement actually is. Is it a resource, a connection, a reflection of deeper, hidden order? Or is it a symptom, a sign that space and time are not what we thought? Some theorists suggest that space itself emerges from entanglement, that the connections between quantum systems generate the fabric of reality, that without entanglement, there would be no here, no there, just unconnected fragments. In this view, geometry is not fundamental, information is. Space-time becomes the result of patterns of entanglement, woven together by mathematical relations. The cosmos is not a place, it is a tapestry of quantum correlations. Others suggest that entanglement may be key to reconciling gravity with quantum mechanics, that understanding how particles influence each other non-locally might unlock the nature of space-time curvature, that black holes, wormholes, and even time itself may be built from entangled bits. The theory of EREPR, proposed by Leonard Susskind and Juan Maldacena, explores this idea, connects Einstein-Rosen bridges, wormholes, with Einstein-Podolsky-Rosen pairs, entangled particles. In this strange proposal, entanglement is geometry. So where does this leave us? With a universe that is deeply interconnected in ways we do not fully grasp. With a reality where distance may be an illusion, a surface phenomenon hiding deeper links. Entanglement tells us that the whole is more than the sum of its parts. That measurement collapses not just a particle but an entire relationship, that the universe may be written in the language of connections, not locations. And as we study this further, we begin to see that our classical notions of independence, separation, and objectivity may not survive, that we are not observers standing outside the world, but participants woven into its deepest code. That entanglement, far from being strange, may be the most natural thing of all. Chapter 24. Inertia, the hidden memory of motion. Why do objects resist change? Why does it take effort to make something move, or to make it stop? This quiet, everyday fact that matter resists acceleration is called inertia, and it may be more mysterious than it first appears. We encounter inertia constantly. A ball at rest stays still until kicked. A moving car resists a sudden stop. A planet glides through space, holding its momentum for billions of years. Inertia is not just about laziness, it is built into the structure of reality. Newton captured this in his first law of motion. An object at rest stays at rest, and an object in motion stays in motion, unless acted on by an external force. This law is not about movement but about symmetry, about persistence, about memory. Why should objects keep moving unless stopped? Why is motion the default? To understand inertia, we need to ask what it is we're really describing. Inertia is not a force, it is the absence of force. It is the behavior of objects in a perfectly neutral environment, and that leads us to something deeper: the geometry of space-time itself. In the language of Einstein, inertia is a reflection of how mass moves along geodesics, the straightest possible paths through curved space-time. In flat space-time, these paths are straight lines. In curved space they bend. But either way, motion without force is simply following the shape of space. Inertia is geometry, but there's more. The idea of mass, that quality which gives inertia, is itself mysterious. Why does matter resist acceleration? Why does one object have more inertia than another? The answer leads us into the quantum world. In modern physics, mass arises from interactions, specifically interactions with the Higgs field. According to the Standard Model, the Higgs field permeates all of space. Particles acquire mass by interacting with this field, like swimmers pushing through a thick fluid. Some particles barely interact and remain light, others interact strongly and gain mass. This interaction explains inertia. The more a particle couples with the Higgs field, the more it resists changes in motion. Inertia becomes not just a property, but a consequence of quantum dynamics. But there's a stranger idea, one that goes back to a thought Einstein wrestled with for years. It is called Mach's principle, and it asks, is inertia absolute or is it relative? Could inertia itself be caused by the gravitational influence of all the other masses in the universe? In this view, a spinning object resists change because of its relationship to the rest of the cosmos. A solitary object in an otherwise empty universe would feel no resistance, no inertia. Motion and rest would be indistinguishable. Mach's principle has never been fully confirmed, but it echoes in general relativity. In Einstein's equations, the geometry of space-time, and thus the paths objects naturally follow, is shaped by mass and energy. The universe itself helps define what motion means. Think of a gyroscope. When spinning, it resists being tilted. That's inertia. But what is it resisting against? What defines its axis? According to Mach, the answer may be everything else. The stars, the galaxies, the distant matter of the cosmos. So perhaps inertia is not just a local property. Perhaps it is a global echo, a memory of the universe's structure, woven into every atom, a subtle tug from the totality of existence, a hidden connectedness in the fabric of motion. This brings us to a paradox. In space, away from friction, away from force, why does an object continue in motion? The absence of resistance should mean randomness, but instead, we get order, continuity, direction. Inertia gives matter a narrative, and perhaps that's what makes it so strange. Because inertia at its core is a form of memory. It remembers the last state of motion. It resists change, not because of defiance, but because of conservation. Conservation of momentum, conservation of energy, conservation of story. When we push an object, we are not fighting its mass, we are fighting its history, its trajectory, its embedded path through space-time. Inertia is not just what things do, it is what things are. In modern physics, especially in theories like loop quantum gravity, motion is seen as a sequence of discrete events, a path through spin networks. Inertia becomes a manifestation of structure at the smallest scale. Even here, memory persists, and when we look beyond, to cosmology, to dark matter, to the rotation of galaxies, inertia plays tricks. Galaxies spin too fast for their visible mass. Stars at the edges move as if held by invisible glue. Either there is hidden mass, or our understanding of inertia must evolve. Some modified gravity theories attempt to tweak Newton's second law, adjusting inertia in extreme environments. These remain speculative, but they remind us, inertia may still hold secrets. It may not be as constant, as clean, as absolute as we thought. So what is inertia? It is the resistance to change, the symmetry of motion, the memory of force, the weight of the cosmos imprinted on every atom. It is the quiet rule that matter follows when no one is looking. And without it, there would be no stability, no planets, no orbits, no predictability. Inertia is what keeps the universe from trembling into chaos. It is what lets the moon circle the earth, what lets us walk, what lets us fall and rise again. A principle so humble, we rarely notice it. And yet, so vital, we owe it everything. It is the pulse of persistence itself. Chapter 25. The Singularity. Where physics breaks down, there is a place where the known laws of physics collapse into silence. A boundary not made of matter but of unknowing, where equations explode into infinities and space-time tears itself apart. This place is called a singularity. At the center of a black hole, at the beginning of the universe, in the deepest recesses of math, the singularity stands as a mirror, not just a point of extreme gravity, but a crack in our understanding, where our models cease to function, where certainty dissolves. Let's begin with the black hole. According to general relativity, when a massive star collapses under its own gravity, it can shrink to a single point of infinite density, a singularity. All the star's mass is compressed into a zero-volume core. Space-time curves so violently that not even light can escape. But infinities like that are a red flag. They signal not a physical reality, but a mathematical breakdown. A place where our current tools no longer apply. Just as dividing by zero gives no meaningful result, describing a singularity stretches our theories until they snap. Time and space near a singularity become warped beyond recognition. The order of cause and effect can reverse. Distances lose meaning. Time itself may come to a halt. It's not just extreme, it's incomprehensible. Hiding this singularity is the event horizon, a boundary in space-time beyond which nothing can return. From the outside, the singularity is invisible, wrapped in gravitational silence. But its influence remains. What lies beyond the event horizon is still debated. Inside, general relativity predicts that all paths lead to the singularity, that nothing escapes, nothing survives, nothing remains unaltered. And yet, quantum mechanics insists that information must be preserved. This leads to one of the greatest unresolved puzzles in modern physics, the information paradox. If things fall into a black hole and the hole evaporates via Hawking radiation, where does the information go? Is it destroyed, hidden, scrambled? No one knows. Some believe the singularity is a placeholder, a sign that quantum gravity must take over, that a future theory will smooth the infinities and reveal a deeper structure. Just as atoms replace the idea of indivisible matter, perhaps singularities will be replaced by something more fundamental. Others think of singularities not as places but as limits, boundaries of predictability, where the initial conditions no longer determine the outcome. A singularity is not a thing, but a question we can't yet answer. Now consider the singularity at the origin of the universe, the Big Bangs. According to standard cosmology, the universe emerged from a state of near-infinite density and temperature. Space, time, and matter all began there. But again, was it truly a singularity, or simply the point where our math breaks down? Before the Planck time, about 10 to the power of minus 43 seconds, our understanding collapses, quantum fluctuations dominate, space-time becomes frothy, chaotic, undefined. We cannot speak of before because time itself was being born. In this early moment, singularities and uncertainty intertwine. The universe was not a smooth balloon inflating, it was a storm of probabilities, governed by quantum laws that defy common sense. And whatever happened then, still echoes in the structure of reality today. In string theory, singularities may be softened by extended objects, strings, that cannot be compressed to zero. In loop quantum gravity, space-time becomes discrete, and the singularity is replaced by a bounce, a bridge from one universe to another. In these views, the singularity is not the end, but a transition. Some theorists believe that information that falls into a black hole is encoded on its surface, a concept known as the holographic principle. The volume is an illusion. The information is stored on the boundary. If this is true, then singularities do not destroy, they transform. There's even a growing idea that the entire universe may be a projection of lower-dimensional data. And what we experience as space and time is emergent, a byproduct of something deeper. And in that framework, singularities are not breakdowns but artifacts, moments when the code runs out. So what do singularities really mean? Are they real places? Are they symptoms of incomplete theory? Are they the ends of physics, or the beginnings of something new? No one knows for sure, but what we do know is this. Wherever singularities appear, they mark the edge, the limit, the boundary between understanding and mystery. And in physics, as in life, the edge is where the most profound questions begin. So we end here, not with an answer, but with an invitation. To wonder, to doubt, to explore. Because every time we faced a singularity, we found a new kind of truth waiting behind it. And perhaps the next great theory, of gravity, of information, of reality itself, will be born from the shadow of the singularity. Until then, take one last breath. Let the paradox settle, let the questions linger. Because physics does not give us certainty, it gives us the courage to ask, and the beauty of not knowing.